Yeah. Test.
Freezes occasionally.
Yeah. Ah, okay. So they say the video freezes for them, but okay. Okay.
So just have them stand up.
It's also super blurry for me.
See that in the camera track.
I see. Okay. Anything else that you think is?
Yeah, there's nothing. I mean, it's everybody in the room. It's either going to be you see the presenter in real time, or you see the people.
Sorry, what do you mean?
It's going to freeze.
For them, you mean?
The presenter might freeze.
Ah, okay.
But the people,
Okay.
there's nothing we can do.
Okay. So you say that there is more prioritization?
Everybody's on. Presentation should be.
I see.
Full
Fluid.
motion.
Yeah. Okay. I see. So it's prioritized. Okay.
Later on, they're going to get because they're recording in the camera. Fix it. So
Oh, okay. I
it's
see.
just
Okay.
not enough bandwidth.
I see.
You understand?
Yeah. No worries. Thanks a lot. Hey, what you? Whatever you want. No, we're doing. Thank you. Yeah, we can take notes. Yeah. That's why I was like, but I don't know exactly what to call or if you want to take notes. If you want to or both of us, we are confusing. But I don't know exactly. Hello? Yeah. Okay, so let me see if I can. Can you hear me, Kerry?
Yeah.
Yeah, we can hear you well. So
Great.
thanks everybody for coming to the RustMC. As we said in the talk, in the Rust for Linux talk on Monday, it's the first time it's the second time we do an MC, a Rust MC, but it's the first time Rust is in the kernel. It's the first year that we have an LPC where Rust is already in the kernel, and we have a bunch of talks that are very, very good. I think you are going to enjoy all of the talks. We couldn't get too much into the technical details on Monday, but the presenters today will give you some real technical details, and I think you will really enjoy the talks, and we have some nice announcements, I will say, or I don't want to spoil anything, so I will start with the first talk. So Gary has worked, he's in the core team of Rust in the kernel. He has experience in the compiler, in the Rust language, in kernels. So he has a lot of knowledge, and he has prepared a new tool that I think you will find very, very interested in you if you are interested in prevention counts, locking, contexts, etc. in the kernel. So thank you, Gary, for presenting and being the first. Good luck, and I think you're on. So whenever you want to start, please go ahead.
Great. So thank you everyone for coming to my talk. So I'm going to introduce a new tool called Kink. It's designed to be capable of detect multiple kind of code misuse, but one of the first links that have been implemented is the compile time detection of atomic context violations. So before I talk about what the tool can do and how to use it, first I need to get into some background about why this tool is needed. So the first is the very important thing is to get the actual term correct, right? When we say Rust is safe, and what does actually mean that Rust is safe? So the safety of Rust is basically its soundness property, which is safe Rust code cannot cause undefined behavior. And in this context, undefined behavior includes dereferencing, dangling null or online pointer, like for example, use of free, or also double free. These are undefined behavior. And buffer overrun is undefined behavior. Data resist is undefined behavior. And break alias rule is undefined behavior, etc., etc. But there are also a few things that are not undefined behavior, which is, for example, memory leak is not considered undefined behavior in Rust. Therefore, safe Rust code can leak memory. And deadlock is not undefined behavior. And similarly, panic or abort are, or kernel bug or kernel panic. These are also not undefined behavior. So they can be triggered by Rust code. It's not saying that these are good, saying that like kernel can panic, right? It's just that in Rust terms, safe program can safely trigger panic. That's just a correctness issue, not a soundness issue. So now we look at some bad code, right? You can obviously this is bad code because you're using a mutex lock while a string lock is being held. This is a very clear context violation. But we all know this can happen by accident, especially when code is complex. We have multiple level of nesting. So in Rust, there's no compile time guarantee that this won't happen. Is this safe? Well, yes, because just as I mentioned in last slide, deadlock is considered safe in Rust terms. So this is bad. It's a correctness issue, but it's safe regardless. But if we switch from spring lock to RCU lock, then things are a little bit different. We can see is this a very similar bad code where it's a context violation. You call schedule when you're inside reside RCU critical section. But if I ask a question, is this safe again? The answer is a little bit different. So just in case anyone's, I'm pretty sure the audience is very familiar with RCU in the kernel. But in case somebody is from more on the Rust side is listening, I'll just give a very brief introduction to the RCU. So this is a very simple RCU use case where just one of the thread is doing a read, and one of the thread is doing an update. But if we look at what this compiles to, if config preempt RCU is off, then you can see the read lock and read unlock is basically compiled into preempt disable enable. If the preempt count is off, then they are just turned into barriers, and which is basically just a compiler fence with no instruction being generated at all. So how does this work? This works because synchronized RCU returns after a context switch has happened on all CPUs. And we know that it's a context violation when you try to sleep inside the atomic context. And therefore, context switch will not happen inside RCU reside critical section. But this only works by assuming that there's nothing guaranteeing that context switch will never happen inside RCU reside critical section. Well, that is if you disable the atomic context debugging. If we revisit this bad code, you can see that sleep inside RCU reside critical section breaks assumption of synchronized RCU. In this case, we get some user for free just by exploiting the context violation without actually trigger any buffer overrun or otherwise. So this is why it's important, because atomic context violation does not only cause deadlock, but it cause user for free, which is a memory safety issue. And if we combine this, right, so this is essentially not only a correctness requirement, but also safety requirement that we never have atomic context misuse. This is fine in C because there's no distinction between safe and unsafe. So you just look at code and say, okay, this is broken because this is an atomic context violation. And well, it might trigger it might trigger CVE, but there's like nothing saying it's bad, but there's no distinction between currentness bad or safety bad. But combining this with the soundness property with Rust, which is basically saying safe Rust code cannot cause undefined behavior and therefore should not cause risk of free. This means that we must not design a safe API that allows Rust kernel code to sleep inside atomic context. And this is very hard, actually. So how can we actually solve this issue? Well, this easiest solution is actually to make sleep unsafe, right? If sleep is unsafe, then context switch is unsafe. Therefore, you can't trigger atomic context violation with just safe Rust code because you can't sleep with safe Rust. You have to whenever you call a function that need to sleep, you have to say safety comment. This function is called outside atomic context, and therefore it can sleep. But this is obviously a bad idea because it's make API design very horrible and unergonomic. Another possible solution is to use token types, which is basically like a dense with type system that gives you all the all the safety without actually having much overhead in the generated code. So in this case, we can have a token representing atomic context and process, and then we use this kind of tricks to ensure that there's only one type of one single token that alive across the whole execution of program. So, for example, if a function needs to sleep, it will need to take a mutual reference of a process context token, so which asserts ability to sleep. And when you lock a spin lock, you have to take away whatever token is given for the atomic for whatever context you are currently in, and transition you into an atomic context. Well, this also, this solves the issue of addressing the sleep inside atomic misuse. But this also basically infect all the functions that need either change the context or have to assert a context, which also is very horrible in terms of usability. We have another possible solution, which is a dynamic check, because in preemptible kernel, we already have a runtime preemption count, and preempt enable and disable will tweak this count. So we can just check this count before sleeping to ensure that we never sleep inside atomic context. We can just, for example, if you try to sleep inside atomic context, we can just turn into a bug. And this is essentially what config debug atomic sleep is doing. But obviously, this is a debug option, and it's not always enabled. And if we can change this to always enable this, but this obviously have a runtime overhead, so which is also not ideal. Or we can have another possible solution, which is just ignore the problem at all. We just use whatever API design that we have currently, and we just trust the developer, like what we currently do for our C code. And we can ask the developer to use logdep and debug atomic sleep when they're developing their program to find out if there's actually a bug. But we just don't always enable it. Well, this is technically unsound in Rust, because you can technically write a safe program. If you do not enable debug options, then this safe program can cause memory safety issues. So basically, we are currently in a dilemma, right? We have three things that we want to optimize for. We want soundness, we want no runtime cost, but we also want an ergonomic API. So if we use token types, then we kind of trade so that we have no runtime cost, and we'll have a sound API design, but it's not very ergonomic. If we have runtime check, it's sound and it's ergonomic, but it obviously have runtime cost. Or if we ignore this, then it's just like our current C code. We have ergonomic API and we have no runtime cost, but it's not sound. So Kink is basically trying to add something in the middle where it's both sound, no runtime cost, and has an ergonomic API. Obviously, this is a very hard problem to solve. So we first need to look at the rationale why Kink is trying to do. So first, we have to recognize that our need does not fit into the Rust safety model, because without complex type system dancing or runtime check, it's not feasible to have an ergonomic API. or like you can't choose all three of these desired properties. But we can extend the compiler to provide what we need. And we are not the first project to do this, because Servo also use a custom plugin to the compiler to do some checking to ensure that GC roots on the stack are properly rooted. So if you run the Servo without this custom plugin, then you can actually get into user for free issues, because the JavaScript side will just free the memory without, if the Rust side is not rooting it properly on the stack. So what Kling is trying to do is to check atomic context misuse during compilation time as extensive as possible. But we always want the developers to get full control of how things behave. So for that, once that can't be checked, we should provide an escape hatch, so it can be either override with runtime check or with an unsafe statement, so that it's like they can actually get things to compile if necessary. So these are 5 design goals of Kling. So at first, have to be very simple to easy to understand, explain, which actually determine that Kling will not just turn your program into very complex constraint and give it to a solver, because that will not give very useful information, and the programmers wouldn't be easy for programmers, developers to understand what's going on inside this tool. It has to provide useful diagnostics, and as I just mentioned in the last slide, provide escape hatch to give full control when necessary. It needs to have a same default, so it requires little annotation as possible, so that it wouldn't be too much friction just to get this tool running. And also, it has to be fast, because we want to make it part of every compilation instead of a tool that you run once in a while or just enable in debug build, like or the debug configs. So here's what Kling is trying to enforce the rule. Each function is given 2 properties. The adjustment, which is the preemption count after calling a function. So the preemption, it's basically the preemption count in the kernel. So Kling is running as if preemption count is enabled, and it will try to track possible range of preemption counts. So each function give one of them is adjustment, which is what's the preemption count after the function is called, relative to the function's entry. And then another one is expected value when calling the function at the entry point of this function. So these are all approximations. So adjustment must be an integer, and so a function cannot return with different preemption counts adjustments. And the expected value must be a range, so it cannot represent things like 0 or 2, for example. Some examples of properties of function is like spin lock, RC relock. They just adjust preemption count, increase them by 1, and they can take any arbitrary preemption counts. I'm ignoring the real-time kernel and the row spin lock here, but in practice, I think it can just be approximated with 2 preemption counts, one for the RT and one for not. And for spin unlock, it's basically decrement the preemption count by 1 and expect to be 1 or higher. This is also very straightforward. And other sleepable operations like music operations, they will just adjust this preemption count by 0, and they expect the preemption count to be exactly 0. So here's how you actually annotate the properties with Kling. So there are 2 types of annotations in Kling. One of them is unchecked annotations, which is usually applied for FFI functions or for functions that you need the escape hatch, because Kling is not cannot infer properties for this function. So for example, this is basically the same as the last slide, except it's using the Rust range notation instead of mathematical notations. So 0 ... means from 0 to infinity, essentially. And in Kling, there's also a check annotation, which is you give a function annotation, and Kling will actually check it for you without assuming it. And this can be more strict than what can be inferred. So if you want to have annotated function to be only callable from atomic context, you can say this expects 0 dot dot, so it expects any preemption count. Therefore, it must be able to call by inside any context. And K-lint is trying to infer for a majority of the cases, so that as little annotation is needed for the developers as possible. And for generic functions, it's a note, because generic functions can have different preemption count adjustment depending on the type parameters. Each monomorphized instance is inferred separately. So you can have generic functions. You can have like algorithms that work on a variety of data structures and have different instantiation, have different preemption counts, and K-lint does support that. There are a few cases where annotation is absolutely necessary. These include FF5 boundaries, and this also include recursive functions, because the K-lint is trying to do things as locally as possible. So it does not want to have all the requirement generated for the whole kernel and then try to solve these. So for recursive functions, in some cases you need to annotate them, but in some cases you don't. In most cases, if annotation necessary, K-lint will actually give you a hint, say you can try to annotate this recursive function with this annotation, and it will just work out. And there's one exception in which it does not have the ability to infer, which is indirect function calls. So this includes function pointers and trait objects. But for function object, currently there's no good way to annotate them. So currently, if there's a violation detected by K-lint across function pointers, it will just give you a warning. But for trait object, you can actually annotate on trait method, so things will just work. So here I want to show you a case study, which is the very first time that I run K-lint on the actual RESTful Linux kernel. And it turns out inference work for most functions. Apart from FFI functions, the only place where annotation is required is on the arc-wake trait. So this is part of the K-async, the kernel asynchronous runtime using Rust futures. I think it's powered by work queues. And as part of this, we have a trait called arc-wake. This is very similar to the standard library wake trait, but we implement this for our custom kernel archetype instead of the kernel standard library provided archetype. So we have our separate arc-wake definition, and this have two functions, two methods, wake by ref and wake. And so by default, K-lint will assume indirect functions can sleep. So in this case, I have to override that assumption by explicitly marking that wake by ref and wake must expect preemption count of 0 to infinity. So they must be callable from atomic context. And the reason for doing this is that wake functions are called from wake up, and in this case, it has a spin lock or row spin lock. I couldn't remember which one is it. But it's definitely inside atomic context and therefore cannot sleep. So K-lint is complaining that these functions can sleep and giving me a violation. So I have to annotate with this annotation so that K-lint is happy. But it turns out after annotating this, K-lint gave me a different error, and it actually is a bug. So this is the error that K-lint gives me. This is actually just a snippet of the whole error, which is 2 pages long, which is one thing that I have to optimize because it's not currently the error message is not as friendly as possible. Can people see this slide, or do I have to zoom it somehow?
I think we can see all of the text. Barely the first line, but we can see it.
Can you not see the first line, you mean?
No, we can. Don't worry.
Okay. Yeah. So in this case, there's actual bug in the program that's being detected, which is if you have an executor and you spawn a task onto it, and you later cancel the task, there's in the code that in the K-async code in the Rust branch, the waker itself actually have a strong reference to this task. So this means if you spawn a task, do something, add it to a wait queue, and then cancel the task, what will happen is that the task will not be dropped. Everything will still there's still one live reference to it. And later, when interrupt happens, for example, and then this task is waked up, this will be the last copy of it. It will be dropped, and in this case, it will recursively drop the task, drop the executor, etc., and which all happens in atomic context. But this method cannot be called inside atomic context. So this is indeed an atomic context violation, and it's I mean it's fixable, but it's not very straightforward. So it turns out this is an actual bug. I originally didn't really trust Kling that much, so I think, oh, maybe there's something wrong with my program. But it turns out this is an actual bug that have to be solved. It turns out even though the tool is still in its infancy, it's already proving to be quite useful.
Get it? 5 minutes.
Right. So this is what the tool is capable now, but obviously it's will have some limitations. So one of the limitations is currently it does not handle conditional lock acquisition very, very well. So for this try lock function, because the preemption count adjustment can either be 0 or 1, depending on which variant is actually being returned. Currently, this is not representable inside Kling. I have some plan to improve upon that. It might take form like this, where adjust can take a expression that represent using like variant. You can kind of switch based on the variant of the return value, but this is still yet to be implemented. I should note that conditional lock acquisition for mutex is fine because it does not change the preemption count adjustment. Another limitation is currently Kling does not read about values of variables. So data dependent lock acquisition also doesn't work. In this case, even we as human, it's very easy to see that the spring lock and unlock can only happen if take lock is true. So either they're locked and unlocked or nothing will happen. But currently, this is not detectable by Kling. So Kling will say, okay, this function can either increment preemption count by 1 or decrement by 1 or change nothing. And this is broken. And so this is another thing that I will have to address, and that's on my agenda. Note that if you use if you use the drop guard pattern, Rust will synthesize a drop flag so that it will take us exactly back into the previous slide. So this kind of pattern also doesn't really work well with Kling currently. Another limitation is with how Rust C currently generates code. So if we have things on the top, we can see there's no case where if let does not hold, then there's nothing to be dropped. But Rust C will currently insert a drop X in this else branch because it's using if let, and Rust C does not see that it's the only case where it's not going to hold will not require dropping X. So Rust C will generate a little drop, and which Kling will see as potentially change the preemption count. So this will also be complained by Kling. This is also something that needs to be fixed. And actually, this is the only factor, I believe, that blocks Kling from wider testing, because Binder has a lot of these patterns, and so Kling currently does not run on Binder code. Yeah, that's all from me. If you want to know some details about how it's implemented, you can either look at the code as a repository, or you can refer to my slide I gave in Congress host, which contains some more implementation details. And there's also a link if you are curious about how servers implement their compiler plugins. Thank you very much.
So we have maybe 1-2 questions quickly. We have to go to the next one. Anybody? No questions? Let me see the chat. We have something. Okay, so you have impressed, I think, everybody. They are speechless. So I think also Kaylin found other things, right, Gary? It's not just one that you found.
Yes,
You
there's.
found, when we ran.
I think I also find a few bugs in the binder code in the early version of the binder. I'm pretty sure Alice will have addressed all the bugs in binder now. It's not perfect code.
Yeah, it
We have
found a
a
few
question.
deadlocks.
Hey, I was just curious how much overhead adding Kalen added to an average build time.
Almost negligible.
Oh, lovely.
It's the code gen time spent on by LVM is basically a magnitude higher than the runtime required by Kling.
All right, good answer.
Thanks a lot, Gary, for preparing the presentation and for working on Kylint and all the other things. So yeah, let's move to the next one. Let me prepare.
Thank you, everyone.
So next, we have Benno. Benno is also a member of the core team. This is the second and last virtual presentations. We had them in the beginning so that if there was technical issues, I didn't mention it before. But yeah, the first one went very smoothly. Hopefully, Benno also goes smoothly, and our virtual presenters are fine. So Benno has, as I was saying, he's in the core team in the Rust subsystem in the kernel. He has been working on init, which is the talk what he's going to talk about. He well, he's an expert, even if he may not say so. He's an expert on the language as well, and he's also working in to improve the Rust language, which he may speak about in this talk in the field projection RFC, which is for the kernel it could be very important for ergonomics for the API that he has designed. So Benno, whenever you want.
Yeah, thanks for the introduction, Miguel. As Miguel said, I'm going to talk about address stability in Rust and also field projection in the second part. So my talk is split into those two parts. First, talking about initialization and address stability, and then about field projection. The first part will involve less Rust, and the second part will require a bit more Rust knowledge, so mileage may vary. Firstly, let's talk about why we would want to use Rust. In this case, we want to avoid memory issues, and as Gary already explained, in safe Rust we can avoid undefined behavior. And if we just pick out a single thing that can go wrong, initialization is a thing that can go wrong, and you would think that initialization isn't actually that difficult, but it turns out that it is actually very hard. I just looked at a few commits here with very crude filtering through, and I found a lot of commits that had fix uninitialized in the title, and they all have to do something with uninitialized memory or something like that. The list also goes on, and I've capped it at this year's issues. But with Rust, we can avoid all of these issues, and we can avoid all of these extra fix patches that we can do. And we do this by having the compiler check our code and ensure that our variables are actually initialized, and we do not run into any problems with uninitialized memory. But sometimes we actually do want to handle uninitialized memory in cases where we need to be very efficient, for example, and initialize something directly or overwrite it directly. And for those cases, we have unsafe code. And unsafe is a bit of a word that might brings a bit of connotation with it, but in Rust, actually, unsafe means that there are certain unchecked operations that we have. And in these unchecked operations, it's easy to make mistakes, similar to C code. So for these unchecked operations, the programmer has the responsibility of taking care of that they're correct. And also this means that if we review some code, then unsafe code requires more thinking and more time to review it. So overall, we try to avoid unsafe code. now that we have the motivation out of the way, let's talk about why we need address stability in the kernel. I'm sure many of you are familiar that in the kernel we have data structures such as linked lists that need to have a stable address because other structures point to our lists, for example. As I was speaking about lists, a list head is just a set of 2 pointers which point to the next and the previous list heads. And if we initialize it, then we point those pointers to itself. But if we now take this whole list head and move it in the memory, so move it to a different address, then we end up with a problem because the pointers do not get updated, but the memory that from which we move them is now invalid. And this means that we have, memory issues. And now that we want to bring Rust into the mix, and in address stability, support in Rust looks like the following. So in Rust, from the get-go, all types are movable. And in Rust, we often use moves. And so in order to prevent moves, we have to use a special API. And this is done by pinning pointers. Pinning means that we ensure that a pointee of the pointer has a stable address. And we do this by wrapping a pointer type P inside of pin. For example, we can take a mutable reference and pin it by writing pin and then mutable reference. And this ensures by the compiler that the pointee has a stable address until the value is dropped. And now you might ask yourself, how does a compiler manage this, that nobody can move the value? Because the standard library provides the following function. This is called the swap function, which takes 2 pointers to values and then swaps the 2 pointees. So if we think back to our list head example, then this would permit us to swap 2 list heads, or essentially to swap an element in the list. And this shouldn't be we shouldn't be able to do that because that is moving memory. And so the logical conclusion that we have to come to is that we cannot give access to a mutable reference from a pinned mutable reference. So you're not allowed to move it because otherwise we wouldn't pin the pointer. Now, if we bring this together with initialization, we run into a bit of a problem. For example, consider this piece of bad C code. We first have a list head variable and then we initialize it and then we return it to the caller. But in this case, we do exactly the thing that we shouldn't do, and that is move the list head. And so this piece of code needs to emit a compile error in Rust because, well, it moves the list head. And often when we want to find a solution in Rust, it often is a good idea to look at existing solutions. And in this case, let's see what C does. You write an initializer function, which just takes a pointer to the list head that needs to be initialized. And then you initialize it in this function. And the user needs to allocate the memory for this list head. If we try to now translate this into Rust, then a direct translation will look like this, very similar in spirit. It also takes a pointer and dereferences the pointer and then assigns the fields to itself, assigns itself to the fields. But if we look closely, this implementation has a problem. We have two instances of the unsafe keyword here. And what you can see there with the star mute is a raw pointer. That is also a piece of the unsafe code. It can be null and so references cannot be null, but this pointer can, and you have to check for all of that. And let's just highlight some more problems with this use of unsafe, who actually ensures that the head pointer that we get into this function is a valid pointer. It might be null, it might be dangling, it might have all sorts of problems. Also, nobody ensures that the list head that we get as a parameter is pinned or stays pinned afterwards the call. So for example, it could be a stack variable. You could initialize a stack variable using this function, and then afterwards you could still move it. So nobody prevents you from moving the list head afterwards. And another issue is that you cannot call or you cannot initialize a list head without using unsafe in this case. And we want people to initialize a list head safely because, well, it's inside of the mutex. And if you need unsafe to initialize a mutex, then most drivers will need unsafe code, and we want to prevent that. The solution in C is to just rely on the programmer to do it correctly. And well, using unsafe in Rust highlights that the programmer needs to do extra work, and we want to avoid people from doing that extra work because, as we saw from the first slide, that is very well error prone. And so with Rust, we aim to offload most of this work to the compiler. Now, to present the safe solution that is that we have upstreamed, let's compare this with the solution that I came up with. And first, I'm going to highlight some similarities. We also have a previous and a next pointer here, and we also assign it to some other pointer that points to the actual object that is being initialized. But other than that, it looks quite different. But most importantly, it does not contain any unsafe code. So if you write this piece of code, then you can be sure that there are no memory issues in this piece of code. It also gives you additional guarantees. So you have to initialize every single field of the struct. If you forget a field, then the compiler will complain and say that you should initialize the field. And the struct will also stay pinned after initialization. So if you try to move the struct after you initialized it, then the compiler will also complain. Also, no uninitialized memory can be used accidentally. Well, just like normal safe for us, the compiler will emit an error if you try to use some memory which has not been initialized. And an additional benefit from this API is that if you, as the author of listhead, decide to only allow you can decide to only allow initialization via pin init. So you can always be sure that an instance of your type was initialized in a pin state and therefore is pinned for its whole lifetime. Another very important thing of this API is that there's no runtime cost. So it's a zero-cost abstraction. So it is just as efficient as if you had written the code in an unsafe way or in C even, and you would get the same output. The API is rather feature-rich. So if you need any help, just hop on by on Zulip and I can help you, or any of our team members can help you. Now that was a bit abstract maybe, and I'll show now a more concrete example from with code from the old Rust branch that we had. And since we already upstreamed the pininit API, we do not actually have this piece of code upstream, but only the beta version that I'm also going to show. And I think you're going to understand why we wanted to have the new solution. So here I'm not sure if it's showing well on the beamer, but we have 20 lines of code here, and
yeah, we can see it well. Yeah.
Yeah. And I'm just going to highlight that we have 4 instances of unsafe here, and you can also see that we have these safety comments that justify why these invocations of unsafe have all preconditions well handled, and but it's well, we still have 4 instances of unsafe. And if we look at what it looks like with the pininit API, then you can see we have no unsafe again. And what is important is that we also have a lot less code and no safety. We have no need for safety comments because, well, we do not have unsafe code. So there's nothing that the programmer needs to manually verify. And what you also might see here is we have 2 calls to functions in this example for every field of the type. So we first have some initial value and then an initializer function or macro that gets called. And in this example, we only have 1 single call to a macro. This concludes my first part of the talk. And so if anyone has any questions about the first part, then now might be a good time.
How does this relate? How does it interact with the standard pin trait and the unpin, the pin type and the unpin trait?
So when you call the pininit macro, you get an initializer returned, and you have to actually insert that into some memory space, for example, into a box, and then you will get a pinned box returned by the. Well, if you give the initializer to the box, you will get immediately a pinned box back. You cannot, well, and that's how we use the pin type there. And the unpin trait interacts with this in the following case. You have to still ensure that your struct is actually not unpin, or for this in order to work.
Any other questions? Yeah, go ahead, Benno.
All right. So for the second part, I'm going to talk about field projections and how they solve a particular problem with pin. And first, let's introduce the concept of field projections. Let's say we have a struct named struct and with a field also named field, and we have a mutable reference to that struct, or in more general terms, some kind of a pointer. And a field projection is a way of turning a pointer to the whole struct into a pointer to only the field. So in this case, we have a pointer to the struct and we a mutable reference to the struct, and we want to have a mutable reference to the field. And we can do this in Rust at the moment. We can just dereference or use the my struct pointer to access the field and then turn this place expression again into a mutable reference. But in Rust, there are many different kinds of pointers. For example, we could use a reference to a maybe uninitialized struct, which then represents represents a pointer that points to a possibly uninitialized struct. And this will only allow you unsafe read access to the value. You can still write to it with safe code, but you cannot read the value because it might be uninitialized. But because you cannot read this value, you also cannot do this projection. But if we think about it, it actually makes very much sense to be able to do this projection. You just, well, the field of the struct might still be uninitialized, but we are only giving you a pointer to which can deal with this uninitialized memory. So we ought to be able to take a pointer to a maybe uninitialized struct and turn it into a maybe uninitialized pointer to a pointer to a maybe uninitialized field. And this last one, as I said, is not possible in Rust at the moment, or at least not safely possible. And we actually would like to have that. The problem with pin is, well, now going to the problem of pin is, if we have a pin type, then all mutating functions of that type need to take a pinned mutable reference. Because if you remember from earlier, we cannot allow access to a mutable reference to the pin type because, well, it is pinned at the moment. And if we would allow you access to a mutable reference, then you could swap the value and it would not be pinned anymore. But if we still want to modify the values, the fields, how do we do that? We have only a pinned mutable reference, but not a mutable reference. So let's take this struct as an example with a list head and a count. And this struct needs to be pinned because the list head is self-referential and needs to be pinned. But how do we modify this count field? The thing that we can observe here is that we have two types of fields. The first type of field would be fields that do not require to be pinned, like the count field. And the second type would be fields that require to be pinned, like the list head. And now we could actually just allow mutable access to fields that do not require to be pinned, and only allow pinned access to fields that are, well, pinned. And in this case, we would have a special case of field projection, which would allow us to take a pinned mutable reference to foo and turn it into a mutable reference to the count field, which is just a mutable usize. And if we want to take the list head field, then, well, we only get a pinned reference because the list head needs to stay pinned. These special cases of field projections are called pin projections because they have to do with a pin type, and they depend on the intended use case. Well, which type of reference you get out at the end, if it's a pinned reference or not a pinned reference, and yeah, they depend on the intended use case of the field, and they're determined on a field by field basis on every struct. As I said before, there are different types, or there are other kinds of projections that we can have. One kind was of the maybe uninit, as I've shown before, but also one could imagine a volatile mem struct, which enforces that all memory accesses are done by volatile operations. And this obviously also affects the fields. So if I have a pointer that allows only volatile memory operations and I project it to a field, then and I also only allow volatile operations on that, that should be an operation that is completely correct to do. And we could therefore allow projections from a pointer to a volatile mem of struct to a mutable reference to a volatile mem of the field. And another important usage that we could use for projection would be for raw pointers. So if we have a raw pointer to a struct, then we could safely turn that into a raw pointer to a field. At the moment, you would have to dereference the pointer, take the field, and then use the adder_off macro to again receive a pointer. And this is an unsafe operation. But the projection could be implemented in a way that's safe, and if therefore we would have less unsafe as well. And additionally, if we were to introduce a specific arrow operator or some other operator, then we would make this very concise and actually easy to understand, because yeah, projections make a lot of sense. I created an RFC for adding general field projection support to Rust, and you can view that here. But I'm also going to show the links on the next slide. So thanks for your attention, and you can follow my work on the RFC here, as well as if you want to use the pin init API as a user space library, it is also available there. And if you have any questions or difficulties understanding something, you can hop on Zulip and also ask in any of the streams if you like. Are there any questions?
No, thanks for the talk. One question, but maybe it's just me not understanding exactly the concept of pinning, but let's say I don't use pin init. Do I see the consequences like at compile time or potentially also at runtime? And the reason of my question is, let's say I need to review a patch. Like, what are the best practices to see, like, oh, this guy should have used pin init instead they didn't, something like that.
So I think the best case would be to just go back to the example that I showed from the Rust branch. You will see it in the compile time at compile time, because you will have to use unsafe. If you don't use the pin init API, then you're forced to use unsafe, because you first have to give an initial value to Rust, because Rust requires you to initialize everything. But you have to use some sentinel value at the beginning, and then you have to call some initialization function, and you are also only allowed to call this initialization function once. And you can see that this unsafe here is because the sentinel value should actually not be used, and you have to first call an initialization function before you're allowed to use this conditional variable here. And this is the convar init macro, which does that here. But you also need this unsafe here to do the pin projection in this case here. So if you see someone who uses a lot of unsafe in their initialization, then you might have a hint that they should use pin init.
Okay, so the flag, red flag is seeing lots of unsafe.
Yes.
Okay,
Yes.
thank you. That's the answer that I want.
So I'd like to add one thing to that. In this case, there was actually an awareness of the person who implemented this abstraction, which happens to have been me. But if the person is actually not aware that they actually need that data structure to be pinned, then that person could actually produce an API that is unsound and wouldn't have noticed, right? So we actually need the awareness of at least the people who are writing these abstractions of these issues of certain data structures requiring to be pinned, right? That is a bit harder to catch automatically, right? But catching it after the API exists just uses. I totally agree with Benno. It's either a compile time thing. If you don't use pinning it, and you should be using it, and it was exported like that way, or you see a lot of unsafe, and that's a red flag. You should fix the API.
That was Watson, the other maintainer of the Rust subsystem, by the way.
Any other questions? Yeah.
You gave the example about the field projections, and the examples, the additional examples you gave are maybe on init and volatile mem, where basically every field behaves like the entire type, right? Whereas with pin projections, you really have to decide for each individual fields whether it follows this or not. So
Exactly.
does it really make sense to put them into the same bucket? I mean, there are already crates like with procedural like pin projections, and to kind of make that more ergonomic, does the arrow type or the arrow operator, does it really fit into that?
Yes. Well, we know about the crates that do pin projections already in Rust, but the problem with those is that they're very macro heavy, and we don't have syn in the kernel, and so we cannot really use those. I know there's a version that doesn't require proc macros, but that has several disadvantages. One of them is that it doesn't really produce any good errors or something. Well, the errors are not very nice to read, but also the macro that implements it is very difficult to understand, and so we didn't opt for looking at that. And we think that if this is implemented on a language level, then with the arrow operator, then you could use it a lot more freely, because when you have when you use the pin project crate, for example, then you have to always also call project first, and then you have access to different projections of there. But if you have it baked into the language, then it makes a lot more sense. And also, as you said, it's a bit different to have pin projections and the other projections that I showed, like maybe init and volatile mem. But I think in general, field projection just takes some kind of object and then projects to some other object, and the parameter of the first object is a struct, and the parameter of the second object is a field. And if you view it in this slide, then you can see that all of them are actually part of the same thing, and we can actually implement it in this most general way.
Okay. And did you say that there's a restriction to using procedural macros in Rust for Linux?
Yes, we do not have the syn crate.
Okay.
So
like parsing Rust code
there is a discussion about having it. There's a discussion about having it or not, and what third-party crates we will allow. But in the beginning, we wanted to minimize the use of macros as much as possible and third-party dependencies, and basically show that it can be done without relying on a lot of third-party code. But yes, having seen another crate is a possibility to simplify that. Okay, so thanks a lot, Benno, again. Both our virtual presenters had a nice, smooth talk. Next is Julia, who I guess most of you already know. We were telling her we wanted Coccinelle for Rust for a long time, and she just went and did it. So she will present her work. Thanks a lot, Julia.
So I'm going to present Coccinelle for Rust. So I'm working on this with Tathagata Roy, which means that he has done like 95% of the work, and I have watched him do it. So, so the goal of Coccinelle for Rust is the same as the goal of Coccinelle for C. We also, if you're interested, we have Coccinelle for C++ that's in the works too. We want to perform repetitive transformations at large scale. So for example, Linux kernel, the implementation of Rust itself is 1.6 million lines of code. The Linux kernel is, of course, 23 million lines of code. And so we need to evolve this code. So we have different libraries in the code. They may change. Or also in the case of Rust, the language itself is evolving, different constraints on the language and so on. And so these trigger large-scale changes in the software. So we would like to provide a transformation language that builds on the expertise of the developers. Our original idea for Coccinelle was the things that developers are familiar with respect to changes is patches. And so patches themselves are very specific to a particular place in the code. They're not very generic. They're not going to allow you to do things at a large scale. So we came up with the idea of lifting the level of abstraction a little bit to result in a thing that we call semantic patches. So this is an example. This is a change in the implementation of Rust itself. You can see it has affected a large number of files and a large number of places. If you just look kind of superficially on the screen, you might not really notice, is this a large scale transformation or not? But if we focus in on the part that actually changes, so now with just the red and green parts, you can see that perhaps there's some commonalities in what's going on. So you do not see, you do see a cursor, okay. So here we have, for example, type of. Type of in the two cases, it's removed and it becomes a occurrence of bound type of. And also you can see in both cases, the arguments to this function stay the same, but then we have a new thing over here, which is what we want to do is we want to take this change, these examples of changes, and make something generic that we can use to reproduce the entire change. So the first step is to remove the parts of the code that we don't care about. So we're going to focus in on those parts that I had marked in color. And then, as I argued just a second ago, those two changes, they're not exactly the same because we have some expressions that are different from each other, but they have the same concept, which is that we want to replace the type of call by a bound type of call, and we want to add the subs identity call. So I'll just drop the second one. We'll just think about the first one. So to make a semantic patch, basically what you have is you have some kind of code that you want to change. And then like a ordinary hunk in a patch, there's some little @ at the beginning that provide some context. In the case of a semantic patch, the context is not going to be the line numbers at which the change should happen. It's going to be some information about what parts of this code should be generic, and then the other parts will have to be there exactly. So basically, in our case, what's important, the parts that need to be specified are the type of and bound type of, and the call to subs identity. All this stuff we have over here with the self, infctx, tcx, this stuff is not very important. We're just going to abstract that away as a meta variable. So whatever the object is, if there's a type of call, we want to change that. And the same thing for the argument of that type of call. We don't really care what about its specific properties. Whatever the argument is, we just want to preserve it in the new call. So we end up with this specification. We say tcx and arg should be any random expressions. And then if we have a type of call for any tcx object with any argument, then we should turn it into a bound type of call with the same TCS expression, same argument, and extra subs identity call out the other side. So this little tiny specification can then do everything or almost everything that original patch was doing. Okay, so obviously it's not useful to just replicate existing patches. At the moment since we're developing Coccinelle for Rust, we're going back and seeing what kind of large scale changes people have done and trying to automate them. So that's what I'm kind of focusing on in this talk. So we have our rule, and it takes maybe updates over 200 call sites. We did find, in looking through the code, we did find one call site that we might have expected would get changed, but it didn't. I realize, unfortunately, this is a bit small and you probably can't see everything, but the code is sort of superficially, it doesn't look the same as the ones we saw before. But if you study it carefully, actually the issue is just that the type of, in the red code, in the removed code, the type of call is in some nested expression. And perhaps the developer felt that if they turned it into that bound type of with the subs identity call after that, things would get too big and they cut things up with a lead. So there's sometimes some minor variations in these large scale transformations. One could decide that either one would just wants to fix this case up automatically by hand, or one could extend the rule to try to deal with it. I would definitely In this particular case, I would definitely recommend the first one. We're not trying to automate everything. We're trying to automate lots of things, and then you can perhaps clean up the rest one by one. So there's just to give a few more examples about what you can express. This could have been written in a different way. If you look back here at our rule, we didn't do anything with TCX. That didn't change at all. And so we don't actually have to include that in the changing part. So what this emphasizes here, where you have TCX, it just stays as it is. And then the type of call turns into a bound type of call. So the point actually I'm trying to make is that we're not line-based like a patch is. We're line-based in the sense that if you put a minus out at the beginning of the line, then everything on that line will be removed, but it doesn't necessarily have to correspond to actual lines in the source code. So if we want to keep some things, remove some things, we can break things up in whatever way is convenient. This has the other additional advantage is if there is any kind of strange spacing or comments or whatever within that TCX expression, then that will just be preserved as it is. And then there's another variation which could be nice to have, which is TCX is not necessarily some arbitrary expression. You might want to specify what specific type it should have. And so we support that as well. Okay, so I'll just talk a little bit about how it all works. So in Coccinelle for C, we had to implement everything from scratch. In Coccinelle for Rust, we are trying to build on existing infrastructure. And so we do not write our own parser. We use Rust Analyzer for the parser. Rust Analyzer also has the option. It's a nice thing. It's an option. We'll give you the option of inferring types like we needed in the last variant. Unfortunately, at the moment, that means that you cannot process your code base concurrently. So that may slow things down considerably. But at least the option is there. And so that's the input. We use Rust Analyzer. For the output, we use Rust format. Actually, in Coccinelle for C, we worked really, really hard on pretty printing. And in principle, that should all go away in the case of Rust because Rust format is already pretty printing. In practice, Tathagata has been working really hard last week to get some examples that I'll show later to work. And I think he's spent his entire time on pretty printing. So it's in principle, it works well. In practice, it doesn't necessarily work well. So the main issue is that the person who made their code, or the code, they might not be using the same version of Rust format that the person running Coccinelle is using. So they might perhaps be using the nightly build version of Rust format. We might be using the stable version of Rust format. Or I don't know, they may have not be using Rust format. I don't know. But we found a lot of examples where if we just blindly ran Rust format on the entire file, then we got something very different from what the people had originally. And so what we do now is we find the place that has actually changed. So we do blindly run Rust format on the entire file. Then we find the place that has actually changed. And then we sort of cut that out from the Rust formatted file. And then we drop it into the original placing, the original code. And so then all of the rest of the code stays exactly as it is, which is what we hope for. I don't know if this works 100%. You may need to adjust some indentation or something like that. But it works better than just Rust formatting the whole thing. So in between the beginning and the end, so in between the parser and the pretty printing, that's what we actually were working on. So we have the Rust Analyzer. It's going to parse the Rust code directly. It also needs to parse our semantic patch, because our semantic patch is little bits of Rust code, but with some extra, I don't know, super sauce or something like that. The Coccinelle part, the minuses, the pluses, and so on. So we have to do something special, kind of some hacks around the parsing the semantic patch to deal with that. But basically what we do is the same as in Coccinelle for C. We have our semantic patch, we have our code. We take our semantic patch and we scan over the code and we find the places where it matches. And when we have a complete match, then we make a change. You can make a sequence of rules. You apply the first rule, it will make some changes, and then the second rule will get applied to the output of the first rule, and so on. So in the rest of this talk, I am going to do, I mean, I wanted to kind of see how we are doing as compared to common changes that people have wanted to do in the past. So I took the software Stratus D. It's a local, easy to use local storage management for Linux. It doesn't really matter what it does. It's just a existing Rust project that exists since 2016, so it's a bit mature. It has a good collection of patches, and it's a moderate-sized piece of software. So I had previously made a tool which is called Patch Parse, and this helps me find examples. So it finds common changes in old patches. And so I tried to find patches that have done the same thing at least 40 times. So then I can try to automate those 40 things. I ended up selecting 13 old commits. They affect between 10 and 94 files, up to a few thousand lines of code. So the goal is to replicate them. But of course, these patches were just people thought all this stuff fit together in some conceptual way. There's no guarantee that there's like a uniform set of changes that people have done. So, but it just gives a way so I can kind of see how things are going, what features we need, what's going on, and so on. So here's some major successes. So we have all the commit does is to replace one type by another type. So there was 2 cases of that. So actually we do quite well with that. So this is just replacing one word by another. You could do it with sed probably pretty well too. These are the semantic patch rules that we need for this case. And then we end up with changes. We end up with changes in use declarations. We end up with changes in method signatures, input types, output types, local variable types, and so on, and also in method calls. So that might seem completely trivial, but actually it's not, because this does not, we have sort of a disadvantage that we're following Rust Analyzer, which is that we're stuck with the abstract syntax tree of Rust Analyzer. And the way that's organized might not be exactly the way that people want to think about changes in their code. So actually not all of these things here appear in the Rust Analyzer abstract syntax tree as types. And so we had to sort of make some kind of mapping between the types that we want, the kinds of syntax that we want at the transformation specification level, and what's actually built into Rust Analyzer. And then again, Tathaggata worked really hard on the pretty printing to make everything come out nice in the end. Here's another one. This is a bunch of test cases. They have a pub modifier on them. It's not necessary. And so then we can remove them all. This was very successful. We took care of 69 changes across 9 different files. It may seem like a simple change, but going and changing all those files, it's kind of a nuisance. And then we have one case where the change did not happen, and it's because there was an extra attribute. So this also raises a question about like what should we be doing? Like when you write your semantic patch, do you expect it to match the code exactly, or do you expect sort of some wiggle room? So in the context of C, we definitely found the use for some amounts of wiggle room. So if you're doing like a null pointer test, in C, you can write it as x equals null, null equals x, or exclamation point x. Do you really want to write all those things in your semantic patch? Of course not. So the semantic patch language would kind of expand your null test into all of those options. So here's another case where we have some kind of need for that kind of transformation. If you specify one attribute, do you mean for it to only match the case with just that one attribute, or do you accommodate other kinds of attributes? So these are things we're thinking about. What should we do in these situations? Here's another case. The main interesting part is the rule up in the upper left. It is a rule. It's a function call. It has 3 arguments, and then the last 2 arguments need to change in some way. And then there's some other small things that happen on the side. So here I say I covered 209 out of 417 changes, so we do maybe about half of the work. There was some other issues. The major issue in a number of these examples that I looked at was things that affect use, and I didn't go into exactly what kind of change on use I should be doing. So I miss a lot of changes in that way. Something that I was not at all aware of Probably you are all aware of it if you use Rust, but in Rust they decided that trailing commas was a good idea. And so perhaps it's a good idea for humans, but it's not a great idea for transformation languages because, again, it's just like this thing with the attributes. Like, should we put the trailing comma in the rule? Should we not put the trailing comma in the rule? Should we have all permutations? Like at the moment, we need all permutations. So I've shown something here, but there's actually other rules that don't have trailing commas and so on. So that's another issue that we uncovered that we need to think more about. Here's another one. This also has a trailing comma issue. So this one illustrates some nice features that we did not have previously. We have ... for the rest of your parameters, so you don't have to actually consider the case where you have 2 parameters, 3 parameters, or 4 parameters. You can just say ... and it's however many. We also have ... down in the method body. This was another issue I was not aware of about Rust. The body could be a plain expression, but it could also be like some lets and then a semicolon and then an expression. And apparently inside of Rust Analyzer, that is not considered to be an expression. That's considered to be something else. And so by using ... then we just don't care about whatever is going on in the body. It will just take whatever there is, because that's not what this rule is concerned with anyway. And then there's another issue that there's a bunch of issues that this one reveals. There's also the problem of borrows. Do you want the variant with the borrow, the variant without the borrow? There's also the issue here we have pub and we have async and we have fun. Some instances of this function only have fun, some only have fun and async, some only have pub and fun, some only have pub and fun and async. So do you really want all of these different variants? So clearly we need to think more about how we can make these rules more generic while still allowing people to get the answers that they expect. So we also have some failures. I'll try to go through these quickly. Things that involve changing the internals of strings or changing the internals of variable names. Coccinelle does not do those things. We could do them sometime in the future if we have a scripting interface like we have for C, but we're not there yet. So that's one. This is another one. It's very unfortunate. This is what's called a disjunction. It allows you to specify 2 possible patterns. So here what we want to do is we want to add default lifetimes if no lifetimes are present. This is in response to a change in the Rust language. So here you have to check, are there lifetimes there already? And if they're not, then you need to add the default one. So you need to actually have the 2 possible cases in one rule. And apparently this breaks our parsing of semantic patches. So we can't do this sort of thing at all at the moment either. This one is also an interesting one. This one we have a function, or it's a macro call. So we do transform macro calls, and we are able to transform arguments of macro calls as well, as long as they're nicely formed as expressions. So that's a new feature recently. In this case, for those who are familiar with Coccinelle already, in Coccinelle for C, we have ... and ... lets you say, here's some code that's relevant, and ... that's going to be following execution paths, and then some other code that's relevant. So we're not supporting that yet in Rust. That's like the next step. But this is an example that actually needs that feature, because these variables that are referred to here are not global variables. These are local variables that should be defined in the same function. So you need to make some connection between some previous let and this actual code so that you use the right names. So in general, I don't think we have much time left, but I'm interested in feedback about other kinds of projects that we could be using to, basically what we want to be able to do is provide the features that Rust developers want to use. So we need to see what changes people have done in the past. So what are some other projects we could be looking at, and what are some kinds of large-scale transformations that people have done in the past that they might be interested in doing. And so here's just in conclusion, basically we have a transformation language. It automates things. It does, at the moment, it does atomic changes, function calls, method headers, things like that. It can work at the type level, lifetime level. We try to support everything. And we're going to be working more on ... and on making things more generic. And the important thing is we have some URLs here at the end, and you can try it out. We have a nice page, thanks to Miguel, on the Rust for Linux project that gives some examples also, as well as the relevant links. So, questions?
Thank you, Julia. We have one from Watson in the chat. Question: how does Coccinelle handle conditional code? For example, code that is excluded by some configuration option in the kernel. Is it also transformed or ignored?
Sorry, I have no idea.
We can write it here. So conditional code, if something is enabled or not via configuration symbol in the kernel, is it transformed or ignored?
Is this a question about C or a question about Rust? Do you have conditionals in
Yeah.
ifs in Rust also?
Yeah.
Okay.
It's,
Cool.
yeah.
It's CFG
So that's
false,
a
for
very,
example.
very interesting question. In C, we try to do what we can with ifdefs. So if the two branches of the ifdef are parsable, we try to work on all that. But we have not considered anything about ifdefs at all in Rust. And since we're working on Rust Analyzer, I'm not sure what we will be able to do actually.
So Rust Analyzer, as far as I know, we, for example, for the kernel, we pass the kernel configuration in the Rust Analyzer file that we generate. So Rust Analyzer at least knows the configuration. I don't know if that means that it only follows the path that is enabled or not. I don't know if it is aware of the other side, basically.
Yeah, so I mean, the big selling point of Coccinelle, a big selling point of Coccinelle for C is that it's configuration insensitive. And so you get your ARM code updated and your x86 code updated, everything. But that might not work for Rust.
To me, it sounds like Coccinelle for Rust is a completely separate project. So there's no overlap where you can reuse. So when you want like ... with the when parameter, you have to re-implement all of this. Okay.
Yeah, so we wanted to use, we actually don't know Rust at all. So we wanted to reuse the parser. And Rust is a big language and a complicated language. And so
what's with C and C++? Does that have some overlap, or is it also like
entirely overlapped?
Okay, cool.
We just throw in C++ constructs into the C parser and try to avoid the conflicts and be different.
Okay. Thanks a lot, Julia.
Okay. Thank you.
I should say Julia and Tatarata. Sorry for not mentioning it before. Alice and Carlos are there. There are some, for the people behind, you can sit around. There are some space available. Can you please close? Yeah. Thank you. So next one is binder, Rust binder. Alice and Carlos are going to present. Carlos works at Google. He's a C binder maintainer. And Alice, she also is an expert on Rust, like Ben and Gary. She is also part of the core team in the Rust subsystem. And also Alice has worked in Tokyo, which is very well known. It's a maintainer of Tokyo, which is a very well known asynchronous Rust runtime. So yeah, please go ahead and give us some good news.
So, thank you for the introduction. I'm Carlos, Alice, and again, we're going to talk about the binder driver in Rust. Let's get started. Let's see. Sure. All right. So a bit of background for people who are unaware of how Binder works. It's, Binder communicates two processes. It's a channel of communication. The main channel of communication in Android. It's basically an IPC with some RPC-like features. And it's pretty old. It's not new. It comes from BOS. It used to be called Open Binder. And then it was completely restructured when it was introduced to Linux via Android. And it's used pretty widely in Android because it's the main access to lots of the framework services. It breaks into multiple layers, mainly the driver portion, which is the binder driver, and then there's a user space library called libbinder, and there's some other abstraction layers on top. It's highly abstracted. This is the main model. There's a service, and then you got a bunch of clients on the left trying to communicate, send requests to the service. And the way that the service is going to handle these requests is it has a thread pool, a bunch of threads, and it's going to try to try to service all these requests from the clients in parallel. And it's going to set up this memory map region so that clients can write their messages or transactions, how we call them in Binder, into this memory map. What's unique about Binder? It has this no in-kernel buffering. So as shown in the previous slide, the client through the driver is going to take this user memory and copy it directly into the server's user memory. No buffering in the kernel, right? This is a direct memory exchange. It also does all the operations via I/O control, including a single, write and read command in a single octal. It implements also priority inheritance. These are sometimes synchronous transactions. So in order to not block the clients, we need to inherit the priority on the server side. It performs this sharing and translation of file descriptors. It has a bunch of object management procedures like weak and strong reference counting. Clients also can subscribe to get notified if a particular service dies, and just a bunch of features. So why rewrite it? What is the problem? Complexity, right? All these features packed into this small little module creates a high complex structure that it's really hard to maintain. There's a lot of risk involved with making changes. So this accumulates technical debt. There's no reward. There's no incentive on refactoring things. And all this leads to vulnerabilities, security issues, bugs, right? We're not going to be able to restructure the code without incurring into some major bug. And this is not theoretical, right? Like statistics are there, and we just get a bunch of bugs that in chain are turning to this high exploits, and it's a very vulnerable code in terms of density, and it's not a ramp down either of a new thing. There's bugs, you need to ramp them down. It's not like that. It's been keeping an average of bugs throughout time. It's stable, and it seems like Binder should be pretty secure because it's part of the Android sandboxing, and which is supposed to be a security feature, and so it's critical that it remains secure. Again, all these complicated features must also be implemented in a fast and efficient manner. And you know, every time we try to tweak things to be done in the right way, there's some sort of performance regression and noticeable performance regression that users, you know, see it janked in their phone or something like that. So it's complicated. If you open up the driver, you'll see that there's this 1,000-line functions. I'm not kidding. It is 1,000-line functions, and you know, similar error handling during the unwinding, and you know, it's tricky, right? Like making changes, refactoring all of this is tricky. We've seen this in the past before. Every time we try to refactor things, there's always a bug associated with that refactoring later down the road. And then there's a fix to the fix and a fix to the fix and so on, right? Like there's this big change of fixes that are just crazy. And yeah, the idea is that, you know, we don't want to keep changing or chasing after these memory bugs forever. So
all right. Thank you, Carlos, for introducing why we want to do this. So now it's my turn. Carlos has talked about the cbinder implementation. I'd like to talk about the Rust implementation. So, you know, we already talked a little bit about this, but, you know, one of the places where I think Rust makes a really big difference for a driver like Binder comes with ownership semantics of pointers. So here we have an example where here on the left, we have real code from cbinder where we have this function. Then at the top, we have this assertion saying that the caller should have a temporary reference. And so if we don't, we catch it at runtime. Or maybe you don't catch it at all. In Rust, you encode this kind of thing into the function signature every single time you take a pointer. And so the code is both self-documenting and the compiler enforces that these annotations are correct. Here's another example. So first we saw function signatures, but the same applies to structs. So here on the left, we have a struct from Binder with a lot of pointers. And then you might ask, okay, so this pointer, does that own a reference count? Is it just kept alive because the code frees one before the other? Is it ownership? Like, what's going on? You can't see that from the code. But in Rust, you can, because you use different pointer types for each case. It's similar with nullability. You know, here we have a comment that says, oh, these can be set to null. But in Rust, we actually have a different type. We wrap it in option to handle that case. And so you know in the struct whether it's nullable or not, and so on. So there are many cases of this. Another case, I think, where the slide speaks for itself, I think. You can't actually see this because the slide was cut off, but this is 1/3 of the cleanup. Actually, it keeps going. Yeah, I will. It seems like it spoke for itself, so I will not go on with the slide. So this is interesting. So, you know, Rust does not prevent all mistakes, right? That Rust promises to make some classes of mistakes a lot less likely. You know, if you have no unsafe, it promises to make them impossible. But you know, in the kernel, we will have unsafe. So for us, the promise is we make these classes of vulnerabilities a lot less likely. Here in Binder, we see that For example, use after free. Those do not happen in safe Rust. We also have out of bounds. We don't prevent you from doing an out of bounds on an array, but still, if you do that in C, now you have a vulnerability. If you do that in Rust, it's just going to call bug. And so, even though we did not per se prevent the mistake, we still made it a lot less severe. So, we wrote a Rust implementation because of these things. It's at feature parity. We have all of the features in cbinder are already implemented in Rust. And it passes all of the tests. And furthermore, we can boot a device and run a variety of apps. And furthermore, we don't just have a working driver that's correct. At least I hope it's correct, We also have good performance. As you can see here, we have some graphs, and it turns out that the performance is on par, at least on this benchmark. It turns out that, we don't promise that Rust will be faster than C, but you should be able to write code that's as fast. That's the idea anyway. And in this case, it took a bit of optimization to get here, but we were actually able to do it. And so, cbinder has also had a lot of optimization. So, it's not unreasonable that we had to do the same. So, yeah, this is only a micro benchmark. There's still a lot of work to be done on the performance front. And we will do a lot more work on this front to also, what actually matters is I click, how long does it take, right? That's what matters to users, right? They don't care about the binder throughput test benchmark. But still, I think it's very promising. Code size. There are some places where Rust is more verbose than C, in part because, well, there are a bunch of invariants that we write down in code, but they're implicit in C. And, there are many reasons. But, for example, on error handling, we spent less code. And it turns out that, in this case, it's about the same number of lines of code. So that's also interesting. Go ahead. This is excluding comments. If you read the IFC, so this code is available on the mailing list in an IFC that we sent out. In the IFC, we outline what exactly was measured here. This is without empty lines and so on and so forth. You can also look at the bottom of the patch set, and you will see that we actually delete more lines of code than we add. So that's pretty cool. And of course, that one is with comments. Okay, but what about unsafe? Because, Rust in the kernel is going to have unsafe. But it turns out that for the case of binder, at least, we didn't need very much. And the unsafe we have in binder is mostly because binder is not entirely written in Rust. This binder has a module called binderfs, where we just kept whatever was in the C implementation. And most of this unsafe code is actually related to talking between the Rust part and the C part of binder. Now, there's also the abstractions, which, for example, this includes the work queue. To use the work queue from binder, I had to write a wrapper around the work queue in Rust code. And there are a whole bunch of these. We call them abstractions. And when you just have one driver in the kernel, then we actually end up with a lot of unsafe, because these abstractions are mostly unsafe. They just call it to C all the time. But these are the kind of things that you can reuse across many drivers. So unlike the red region, which is per driver, this yellow region does not scale with the number of Rust drivers. I think, no. So in some sense, you only have to get the work queue bindings right once. So one of the friends from my office, I was telling him about all of the many different things that Binder does. And this is what he had to say. So yeah. Now, this is where I had intended to end the talk. But during Plumber, something happened that I have to address. Because we received an email from one of the vulnerability bug hunters that have their name on several of the cbinder vulnerabilities. And they found a vulnerability in the Rust binder IFC we had sent out. So yeah, this vulnerability, it's some sort of logic error where when you send a transaction, we make some changes, and then we find out that the transaction is actually invalid, and then we undo the changes in the wrong way, basically. And it turns out that cbinder actually had a vulnerability which is almost the exact same vulnerability. So we can compare them and see what went wrong and what was the consequences in C and what were the consequences in Rust. And what happened in C is that by triggering this problem, you can pretty easily get to a use after free. So now you have a use after free in the kernel, and I'm a security person. As far as I'm concerned, it's game over. In Rust, we did not end up with a use after free. There was no use after free, no out of bounds access. What we had instead is that it was a logic error, and we don't promise to prevent those. And we end up, there's this mapping from these IDs to these objects in the kernel, and we could change the mapping for a different process so that it gets confused about which IDs correspond to which objects. And that's pretty bad. Like, in the end, this vulnerability is actually a pretty bad vulnerability, and it's probably also game over. But I think it's a good example because we saw that in Rust, we actually prevented the memory safety part of it, which is what we promised. In this case, there was also a logic error that we didn't prevent. But I still think it's really interesting to see that in some sense, this vulnerability was less severe. I think at least it was harder to exploit. So yeah. All right. Thank you for your attention.
I was wondering about the optimizations. Is there anything general that you can say about the need for optimization?
Optimizations?
Yeah.
So I think, so there's one place where we have a situation. I think the benchmarks I have for this are a bit crafty, and I think I have to redo them. But at least I found that, there are a bunch of super small functions like refcount inc that are written in C and can't be inlined into Rust without something like LTO. And at least on my crafty benchmarks, this rewriting them in Rust did so that they could be inlined seemed to make a difference. But yeah, so I think this falling into C for super small functions is an interesting wrinkle where, there's actually, a question here. Do we rewrite these functions in Rust? Because, this is an extra maintainability burden, right? Now you have two versions and you have to keep them in sync. But maybe it's necessary for performance. So, yeah.
What are some of the learnings that you can give back to the community? This is one of the bigger Rust projects in the kernel right now, or the largest, I think. what have you learned along the way, and how can the community, focus this effort on including more Rust?
I had to write a lot of bindings for different things, and I think it would be nice to, I think you have to, when you begin, like the places where you begin to use Rust, that should be the places where you get the most bang for the buck, like the places in the code that are the most critical. And then, of course, at some point, I'd like to see drivers that are simple, but maybe still done pretty quickly. Maybe we could also write those. I don't know. Yeah.
Thanks.
You mentioned you had a ton of abstractions, and that's kind of part that you added. You said on the slide you had to write them once. So I was wondering, during the course of your write of binder, did the C side of the APIs change that much? And then did you have to go make adjustments to your abstractions?
Oh, whether the C side changed while I worked on it?
Yeah.
The freezing stuff did, like with process freezing, I think. I think that was the only thing that changed.
Okay. In general, when the change is made on the C side.
Yeah. So there was some change on the C side for how process freezing worked.
Yeah.
But I think that was it.
Okay.
So I've been working on this for a year now. So over a year, we had one place. So I think that's interesting.
Yeah, not too bad.
Just to make things clear, the last patch set completely deletes the C version. So there's no parallel intention of maintenance.
Right. I'm talking about the Rust abstractions to the other kernel APIs that you're using, right?
So one note that is in general what we want to do, and this is a common question that we get, right, for abstractions in general in the kernel. What we want to do is, and what we are doing, and we are asking maintainers is, we go to the maintainers of the actual C side, and they are the ones that have to say yes or no, and we want that they maintain the code. So when they know when the C side changes, and they know they have to update the Rust side. And for example, I talk about that in Monday, but one example is, for example, Matthew Wilcox was, for example, happy to commit to maintain both sides, even if he had to re-implement some functions on the Rust side, because he said, well, I will implement it and I will just keep it in sync myself. So that's basically the best case scenario. And that's what we aim for. We need the maintainers to be on board.
Yeah.
So I had a question. Suppose that you upstream the work queue abstractions, right?
Yes, the upstream.
So that's pretty cool. But suppose now I want to change the way work queues work. And being, one of the old dyed-in-the-wool kernel developers, I don't really understand the Rust side of it, and I don't know how to fix that part of it, and I break it. Right? Whose problem is that at that point? How does that get fixed? How do we address problems like that are certainly going to happen at some point?
So I think the general answer is the maintainers of the work queue, in this case, Tejun, needs to be aware of the changes when he receives the patches, and he has to have some knowledge on the Rust side to fix, if needed, the other side. So in the end, we need the maintainers to know some Rust, at least, to be able to change the Rust side as well. So if it is someone that is not a maintainer and wants to change the C side, then yes, then there is a chicken and egg problem there, where we need developers to start learning Rust if we want Rust in the kernel to succeed and to be maintainable. So in the end, we expect that kernel developers, if this is successful, we expect that there is some level of Rust knowledge in most maintainers and also developers, if possible.
So someone asked about positive fallout and what Alice had learned, and at least I know that I've been using the work queue bindings that Alice did to the patterns she applied there in designing abstractions for other things where we have these intrusive structures. So that at least is something that has come out of it and is reusable across different APIs.
Yeah, I just wanted to say, are we planning to nominate a Rust maintainer and a C maintainer for some subsystems?
So some systems do actually may actually want to do that. And for example, I think in NetDev they are going to have a new maintainers file entry, where they will list the people responsible for the Rust part. So in that case, it's another solution for what John was asking. And in that case, if you have somebody that at least knows the Rust side, then the only thing that you need, which maybe is still too much, but the only thing you need is communication between the two sets of maintainers, and be aware that basically the Rust side, in the beginning, I would recommend that they review all the patches that go to the C side in case somebody forgets to update the Rust side, right? Some cases, of course, are obvious because it breaks the compiler will complain. Others are more subtle, so you can still break things and you don't detect them if you change the post conditions of a function in the C side. Of course, you need to change the Rust side if you rely on that, right? So there are several, it will depend case by case. The maintainers of each subsystem needs to decide how they want to approach it if they want to start using Rust in their side of the kernel. I think everybody probably wants to go to break. I guess nobody is going out, so this is, I guess, they really, really want to hear what is going on, but I don't want to keep you here for the break. We have some minutes in the break. There is one question for Nick. And this, let's say, the last one.
I was curious, is cross-language LTO something that you've done performance testing on yet for binder throughput tests?
So, yes, but I think I'm not sure whether my benchmark was correct. but on the benchmarks, I did see a difference, but I've since gotten a little confused about what was going on. So I think I have to redo them.
Okay.
So if you stick around for the next talk, there's also some LTO stuff.
Oh, cool.
Miguel, how long is the break?
I was going to be here earlier, but I had an issue when I was
That's my
Ah, it's yours.
It's
I thought it was
my-
Alice. Sorry. Give her 1 more minute. Oh, we are resuming after the short break. Well, people is still, I think, realizing that we are starting. The next presentation is about the NVMe driver, the work that Andreas has been doing for the past year, I think, or more. Yeah. He has, well, he works at Samsung. He's part of the core team of the subsystem, the Rust subsystem. He also teaches Rust at Samsung. He's trying to increase the knowledge of Rust at Samsung and spearhead that. And he also works on he has also sent to the main list the Null block driver. And yes, I think this is going to be another very interesting talk with some results, I think. So whenever you want to start, Andreas, thank you.
Thank you, Miguel. Thanks for being here for my talk. And if you have any questions, please interrupt and raise them immediately, and then we can service those questions, because I think I have probably too much material, so there won't be any time at the end. So just go ahead and do that, and we can have it a little bit interactive. This is going to be like a little bit of a status update, and then I have some discussion points as well. So the block layer Rust binding Rust abstraction project is the goal with that is we want to allow implementation of block device drivers in Rust. So Alice just covered why doing so, at least for Binder, is a good idea. That was heavily focused on security. And when I talk about abstractions for block device drivers with people, one of the responses I get is it's not user-facing and it's not as security critical as many other parts of the kernel. So why would you start in that particular area? But when we build code with Rust, we remove a lot of bugs. We prevent an entire class of bugs from happening, and that means we spend less time fixing these bugs. No matter if they're security critical or not, we might spend a lot of time hunting with race conditions. And we hear a lot about maintainer burnout, so that ties very well into that as well. The less bugs we have, the less time to review patches from maintainers. And so we also want to provide reference implementations for if you want to go about and build a block device driver in Rust, how do you do that? We want to provide some material you can look at to get an idea of how to do it. And we also want to provide the existing storage community with something to look at. So by implementing stuff that the community is very familiar with, they have some starting point for the Rust stuff. Because one of the blockers for having Rust in a lot of places in the kernel is we need the maintainers to be able to review the stuff that they have in the subsystem. And so by providing these reference implementations, we can help further that. And of course, we want to remove risk for early adopters. If someone wants to build a block device driver in Rust, they don't have to be the first ones to do it. We show that we have a lot of infrastructure to do it, and they can just go ahead. So the block layer abstractions are in 4 parts. We have the actual abstractions. We have an NVMe driver. We have a null block driver, and we have a ton of dependencies for accessing various parts of the kernel that we need. All of the patches are rebased 1 or 2 times per kernel release, and you can find them. I put a link and some branch names. So they will be available as a kernel is released. This is a list of the dependencies, the Rust abstractions that the NVMe driver needs to function. So we have like device abstractions, bus abstractions, IRQ, PCI, IO memory, all of that stuff. The reason I have this list, there's a couple of reasons. One is to say, like when you build a driver in Rust, you don't actually just build the driver because all of the infrastructure you need to build the drivers is missing. So you have to put that up as well. And so I know that some other people are also building drivers that depend on the same abstractions, and we each have like our own copy of these, and we each maintain them on our own. I have it on my to-do list to reach out to people to sort of see if we can crowdsource some of this maintenance, have a common tree somewhere. I didn't get to that yet, but if you're sitting here with an idea to build something that relies on some of this, maybe we can share the load of rebasing this, and also to let you know that this exists and is rebased on top of latest Linux as it's released. So if you are thinking about starting a project, but you're like, I don't know, because maybe PCI is not available in Rust, it is available at some place. And yes. So there was a question, is this intended to replace the current NVMe upstream? This NVMe driver is a reference implementation. it only covers PCI transport, so it doesn't cover like data center uses. It would only work for like your laptop or your local workstation. And in regards to whether it can be upstreamed or not, I have received a very clear knock on that. So that's a no. And of course, I don't agree with the storage community on that, but like it's not my decision, and they have valid reasons for not wanting this upstream.
Andreas, one question from the chat. Benjamin says, not sure I understand the scope.
Yeah, I just addressed that.
Sorry.
I think, let me know if I didn't.
You see it there, the chat?
Yeah.
Okay.
Yeah. Okay. And so even though this particular driver is not currently looking like it's going to be upstream, all of these abstractions and all of the work I do in rebasing them, they have validity in the sense that Rust is coming to the kernel, and I cannot imagine a future where we're never going to access PCI from Rust. And so therefore, this is not wasted work. Like we're still going to use all of these abstractions in somehow. Maybe not from this NVMe driver, but there's many drivers you can write. And yeah, I think, yeah, question?
Just you said you got a knack. Was that like only when there's a user will take this, or does
So the storage community does not want this particular NVMe driver in the tree.
Okay, but once there are, it wasn't like the PCI layer said no.
No. I did not talk to PCI maintainer or for the matter of fact any of the maintainers of any of these subsystems.
Okay.
But like they're not going in unless there's a user. It would be dead code, right?
Yeah.
So yeah, but I'm keeping it alive in my little tree. All right. So we also have, I have the Null block driver, and that has a brighter future upstream. And there was no knock for that, at least not for all of the community. So that's more like a maybe. And let's reevaluate in the near future. And for that, we have radix tree abstractions, and we have some timer support. Yeah, just for completeness, most of the NVMe driver was originally written by Wetson, along with a lot of the abstractions. I've written the Null block driver and some of these radix tree and timer abstractions. So they are available as well. Yeah, Andrea, that's a question.
One question. Let's say I want to use one of these abstractions for my driver. Would you recommend to like pull them from your Git repository, or I don't know, are they applied to the Rust for Linux branch, develop branch, or something?
They are applied to my tree only, but they are rebased on top of latest released Linux tree.
But
so,
you don't rebase on top of the next Rust for Linux next.
I haven't done this rebasing process for a long time. But what I've ended up doing is rebasing on top of kernel releases, and then when Miguel sends a pull request up, after a while he switches back the RC, and then I rebase on top of that to be ready for the next. Yeah.
Okay.
So I'm not committing to doing that all the time, but I will commit to doing the releases. Usually I do the other thing if there's like a patch I need, so I'll get that. So as I said, the NVMe driver is PCI transport only, and it's a good reference driver for a block layer driver because it touches all of these subsystems that we saw before. It's an actual real application. And it's super important that I have that when I shape the block layer abstractions, because I actually had situations where working on Null block, I did something smart to increase ergonomics and safety of the bindings. But then, like in rebasing NVMe on top of those changes to sort of keep them in sync, I find that okay, this stuff doesn't actually work for real hardware because of the way callbacks work when you get an interrupt for hardware or something, and so. Doing the like dropping NVMe and just doing the Null block, that's not viable because we're going to get abstractions that are not shaped correctly to handle real hardware. And so I put the NVMe driver sort of in a maintenance mode while I focus on the null block because of bandwidth issues in my work time. But these are the benchmarks for the NVMe driver for the latest rebase. What we have here is the blue one is the C NVMe driver, the green one is the Rust driver, and the dark green one is Rust with LTO enabled. And in order to, so this is in absolute numbers, IOs per second, yeah?
Cross-language LTO?
Excuse me?
Cross-language LTO?
Cross-language LTO. It's, I have an issue that I can't boot the kernel with LTO on my real hardware. Works fine in QEMU, but for real hardware, it doesn't boot. So what I do is I only LTO the modules, and I sort of hack the build system to only LTO the modules that I want, because LTO breaks down for some modules that, like crypto, that has inline, or not inline, but assembly files in it. So yeah, that's what it is. If you, I have the patches if you want that. I didn't put it out because it's not pretty. Yeah. I reshaped these numbers relative. So now we have performance of Rust driver minus performance of C driver divided by performance of C driver. So relative performance, and the error bars are 99% confidence intervals, and this is 30 samples. So we have not too much noise in the numbers. And so what we're seeing is that for a smaller queue depth, the Rust driver performs up to 5 to 6% worse than the C driver. But for queue depth 16, we actually perform like 1 or 2% better. And that's statistically significant, this improvement. And so I also have something going on here for queue depth 4 that I can't explain. I have no idea about what's going on here. So, but I want to look into that. If anyone has any pointers, maybe you know, speak up or find me later. That's this is dark magic is happening here. Yeah. So yeah, also because the change is significant and permanent. It's not just like a fluke of the run and thing. Let's see. Yeah, switching over to the null block driver. This is the current list of implemented features. We have so only block MQ support, direct completion, soft direct queue completion, timer completion, and read and write requests. No trims or discards. Memory backing, and it's really like a small kind of toy example in the sense that it's only 210 lines. We just heard from Alice before, who had 5,000 lines, I believe, or something for binder. So this is like pretty small and concise, which is exactly the point, because it's supposed to be an easy read. So most people should be able to take it and look at that. We are looking into having parity with the C version, and there is an amount of work in front of us. A lot of these features are like just half day to implement, but some of them is significantly more because we need to bind to various interfaces in the kernel that are not covered yet. And as we heard earlier, when we do bindings, we need to make sure that, or abstractions, we need to make sure that in no possible way can the user of these abstractions trigger some undefined behavior. So we do have to think twice when we do this. These are, so I'm sorry, the graph is a bit small. I tried to make it as large as possible. This is performance numbers for null block. It's FIO running with the IOU ring, and we have the random read and random write. I believe read on top, write on bottom, and then we have each graph is a different queue depth increasing to the right. And each cluster of 3 bars is 1, 2, and 6 cores submitting IOs to this null block driver, memory backed, and direct completion. And so what we see here is sort of opposite of what we see in the NVMe driver, namely that I forgot to mention, on the x-axis we have increasing I/O size, so larger I/O submitted per request. Here we see that we have a very good performance on the smaller block sizes, but as we go to larger I/O size, the performance drops a bit. And but still, the performance is within. I think when we're worse, we're within like 2%, and when we're better, we're within like 10% better. So it's I think that's fine. These are like 40 samples of each benchmark, so they should be okay in regards to noise as well. So if you are interested in contributing to this project, there's many opportunities, especially if you happen to be very familiar with the block layer. I would appreciate any input that you can give, since like I started looking and reading the block layer code like a year ago or something, so I might be doing something that's to some people obvious a bad idea, and I won't be able to see it. So if you have that kind of knowledge, that's a great contribution, and I would really appreciate that. If you want to help participate in building some of these features for Nullblock that we're missing, or even for NVMe, just reach out and we'll coordinate and we'll figure something out so we don't step on each other's toes. And also all of the dependencies are something I lifted out of the old, now deprecated Rust branch, and they are not, all of them are not thoroughly reviewed and verified to be sound. So if you have that kind of inclination, you could also look at that, bring them up to date, make sure they are of high quality. And if you share dependencies with the block layer bindings, please reach out and we can figure something out, or maybe I will hunt you down if I get the time. I think. Any questions? Yeah.
No, 5 minutes.
5 minutes. Okay. So I have the last part of my presentation is a demonstration of a timer API that I have put together with a little bit of help of Bakun and a lot of help from Alice's work queue bindings. I basically lifted the patterns that Alice is using and applied them to something else. So the purpose of this next session is for me to get feedback on this API and to make spread awareness that it exists, and sort of tutorial-like. So this is going to be not the implementation of the API, but how it's used. So this, and the purpose of this is if you have if you want to run a callback on a timer after some period of time, you can use this. That's what I use for the timer completion for the IOs. You define a timer by embedding a timer structure into a place. In this case, we have just some struct that has a flag, and then it has our timer. And you can see we are using the pin init API that Benno was talking about earlier to initialize the structure. So we have a macro that allows the abstractions to go from a pointer to the timer into, basically it's a container off thing, or go the other way. And the macro is implemented in such a way that it cannot, it's always sound to use like this. If you don't have the right type at the right place, it won't compile. You implement a trait on your struct that has the timer embedded, and what you put on that is a run method, and that's going to be your callback when your timer expires. In this case, we're just going to print something and set an atomic flag. And so to create the timer, the struct that contains the timer, we're using the pin-init macro to create an initializer function that allows us to initialize this struct in place. Looks like this. We create a new timer structure, and we create a new atomic boolean. And to tie it all together, we initialize the structure on the stack in place with the stack pin-init. We grab a reference to our flag, and then we schedule the timer some amount of nanoseconds in the future. And in this case, it's just a simple test. It's going to loop until this flag is set by the timer, and then the test will complete. That's it. Yeah. So you can find the timer abstraction and this example as a K-unit test, in fact, in my null block branch. If you're interested in that. That's all I have. Any questions?
So, if nobody says anything, I want to point out that the results are, I think, very nice. The performance results are very nice so far. And some people last year were very impressed with them. And I think you're doing a great job at, let's say, fighting a bit the upstreaming. You have quite a fight. So I appreciate that Andreas is keeping up the good work to make it happen, nevertheless.
Yes, it's great work, Andreas. So I have a small question. How much does the size change if you enable LTO? How much is the code, the generated code size change if you enable LTO?
That's a good question. I don't know. I didn't check, but
okay.
I will. Yeah.
Okay.
A good point. So when you enable the LTO, so one thing I didn't talk about is I also have the helper functions that we used to call the C methods, static C methods and stuff. I have a separate file for the NVMe driver because otherwise these would be linked into the VM Linux image, and then they won't be inlined. So if you have them in your own object, Clang will be able to inline it to the right positions, and that probably increases code size. I would guess, yeah. Yeah, so it could be like a cache code size, or like instruction cache artifact.
Yeah,
It could be, yeah. Okay. Thanks a lot. Thank you.
So next we have Daniel. Daniel worked for Collabora. He works on video codecs. He's leading basically the chart on getting Rust into video codecs. That, as we know, well, it's a huge complexity thing to parse and to handle, right? So Rust may be a good thing there. So.
All right. Thank you very much. So hi everyone. My name is Daniel Almeida. I'm with Collabora, as Miguel said. And I'm here to talk a little bit about moving forward with Rust and Beautiful Linux. I wish I had all the answers. I have more questions than answers, to be honest. But I want to say I'm going to be speaking for 10 minutes. And then I want to use the rest of the time for basically discussion. So very quickly, I want to go through what I have done so far, because I submitted a patch set earlier this year to the mailing list with some very early stage support for Rust and Beautiful Linux. And what exactly is there? Well, we have some abstractions for some of the Beautiful Linux 2 data types. We have a very basic video buff 2 abstractions from which you can spawn a queue, and you can allocate buffers, and user space can basically allocate memory and talk to the device. You have abstractions for some of the video for Linux ioctls, which is where most of the work happens in video for Linux. Things like enumerating the formats, setting formats, telling the device to start decoding, and so on and so forth. We have the code to get the device to probe, which in and of itself is not trivial. And we also have a sample module. And the thing that the sample module does, on top of all these other things, it basically probes. And whenever user space can talk to this driver, and whenever it's processing some ioctl, it just prints to the terminal, hey, I'm processing this ioctl in video for Linux. And it just prints a message, just a print line statement there. But it probes successfully. And also, why do I think we should experiment with Rust in video for Linux? I think there are two main reasons, right? The first reason I'd say is that, well, the media subsystem is not like the scheduler. It's not memory management. If the media subsystem, if there's a problem there, it's not critical to the OS. It doesn't bring the whole thing down. And the other problem, I think, is because video codecs are pretty complicated. Specs for video codecs, they're huge. They're full of details and perks and everything. And the attack surface for codecs are huge. And using Rust, I think that we can basically make some of the vulnerabilities not possible at compile time when we're doing drivers for video codecs. And video for Linux in particular, I know of some areas that are low risk, and they are low-hanging fruits that we can basically experiment with. So, and I discussed all this with the media maintainers back at the Media Summit in Prague, and they gave me some feedback and some roadblocks as well. So I think the very first thing with the media subsystem recently is that the subsystem is overwhelmed. There's a whole bunch of patches going on. There's not enough bandwidth for people to review. There's not enough reviewers, and people are like, they're a tad busy now. So they're like, okay, Dan, to start off with, we can do this, but not right now, not today, because we're sort of swamped. And one of the things that at Collabora we've been doing to sort of help out with this is that we're making some engineers available to work on reviewing patches in the media subsystem. This is one thing that we've been doing in order to increase the bandwidth of people basically reviewing patches. And it's one way that Collabora can contribute to sort of help with this problem, right? Which is a whole lot of work for not enough people in the subsystem. So as I said, not enough reviewers and maintainers. And some people, they actually told me there's another problem. So particularly with things like the media controller API, which is now a central piece of video for Linux, because we have devices like cameras, which they're very complicated, and we use this graph API to sort of expose them to user space. And I had some feedback from the media maintainers that, well, in this graph API, we already have some lifetime issues. We already have some underlying issues in the C code. That's what I'm trying to say, that nobody has fixed yet. And then you're trying to add new things on top, and you're not really sure how this is going to work. So we should think about this before we can do Rust code on top of the C code, basically. They also have a huge fear of breaking their C code, which I had to explain to them that this is basically not possible. Just from the way we work, we never touch C code directly in a way that can break it. And they also said that then we need more people working on this, because if tomorrow you disappear, there has to be another person basically working with you. And Collabora can also help with this, because Collabora can have, in the future, if this works out, Collabora can maybe have more people working on this. But the situation now is the following. Everybody is waiting on everybody else, and nobody really is moving. And I feel that this effort is blocked. And I dislike this. I want to write codec drivers in Rust. I think this is the future. So I am proposing, which is what I want to discuss here, I want to propose this thing. I want to write a virtual stateless codec driver in Rust. Why do I want to do this? Because I think that if we write a virtual driver in Rust, then it's not much more effort to write a real codec driver for real hardware. Plus, if you write a virtual driver in Rust, then we move away from the current state of affairs, which is we're discussing a bunch of things, nobody has source code in hand, and nobody can really nobody can really discuss what they like and what they dislike. We're only on the realm of ideas. And it turns out that we already have a similar driver in C, which I wrote, which is called Visal. So the Visal driver, again, I hopefully you guys understand what a stateless codec driver is. It's a driver in NVIDIA for Linux where you send the compressed data, and you also have to parse a part of the compressed data that we call the metadata, and you have to send this metadata to the driver separately so that the driver can decode. It's basically a driver that takes both the compressed data and some instructions on how to decode that from user space, basically. And we already have a similar driver in C, which is the Visal driver. And what Visal does, is basically Visal, GStreamer or FFmpeg or other user space apps, they can talk to Visal and then start submitting data and metadata to Visal, and they don't think that they're decoding data, actually. But Visal isn't decoding anything. Visal is using debugging tools like ftrace to dump things to ftrace, to dump things to debug FS, to dump things through the VFL2 task pattern generator. It's just a debugging tool, basically. But user space, of course, doesn't know this. It's a driver that, as far as user space is concerned, works like any other real driver, any other real codec driver. So I want to do a subset of this in Rust. I want to take all the debug FS, all the ftrace stuff, all the task pattern generator stuff away from this because we don't need that for a Rust driver. And I want to have a simple driver that probes in Rust that user space can basically talk to, and user space can actually send data to this driver in Rust and receive data back as if this data was decoded. But there's no real hardware. It's only a virtual driver, like Visal. And why do I think this is important? Well, because in order for us to have this, this virtual driver, which I'm speaking of in Rust, in NVIDIA for Linux, a whole lot of things have to happen first. So we have to have the abstractions for important VFL2 components that we are also going to reuse for real drivers. So we have to have abstractions for video buff 2. We have to have abstractions for M2M. We have to have some abstractions for the media controller. My point being, we have to have some abstractions for this driver, which real drivers are then going to use. So this moves the ball, so to speak, forward. This moves the state of affairs further, basically. So it's not much more effort to write a driver for real hardware. It's going to show the NVIDIA for Linux community how a Rust driver will look like in their subsystem. It's not a critical component. If this thing doesn't work, we can just cease working on it, and maintainers will have actual source code to assess, to judge, to see whether that fits within their subsystem. Basically, that's my point. And eventually, if this driver starts to be accepted and people think that this is a good idea, we can deprecate Visal and we can have this Rust driver instead. So this is the plan that I have to move the state of affairs in NVIDIA for Linux. And I wanted to discuss this. I wanted later in a few minutes. I want to hear from the audience what you guys think, if this is a good idea. And also I have a few open questions. So the first question has been asked here a few times already. What happens if the C API is changed and it breaks Rust code, which I think was the question Jonathan asked previously. And can we detect this automatically? I know that this is not possible currently, but I think when I was talking to the maintainers, to Hans tomorrow, to other people, that was one of the major issues. Like, they do not want to get blocked by the Rust code. So they're like, what if something breaks and we can't produce a fix in time? This is going to break or delay everything. So one of the things that I propose is to have a separate kconfig, which basically this driver is going to be behind, such as like media experimental or something, or expert, so that you do not enable this. And if you do enable this, you know that, well, you can break your code basically. And the other thing I want to do is to have a Collabora maintain branch where the community is going to have the latest and greatest code and abstractions and everything in order to develop in Rust for NVIDIA for Linux. And it's also another thing that I want the audience's opinion on, whether this is it's a good idea, whether this adds value, basically. And the other question I have is if there's anything that you think we can do in order to drive this forward. This basically concludes my 10 minutes. So.
Hi.
Can you stand up?
Oh, yeah. So the question I kind of have about doing a driver that's already in the tree is what do you do when they say, well, we already have that driver in the tree. Why are we going to take this one? I worry about doing things that are already existing in the tree in Rust because it's an easy out for people to say it already exists. We don't need it in the tree. That's my only concern with that strategy that you.
This is a strategy that's been looking that other Rust programmers in the kernel are also looking for. And what Miguel said is that
I understand that's a strategy that can work. I would be open to that strategy. In my subsystem, I'm questioning whether the subsystem maintainers are open to the strategy in the v4l2 subsystem, and that's not something I would be sure of.
So they have to say yes, as we know. But I'm pretty sure from what I have talked. Yes, I met Manuel. I was with him in Prague. So I'm somewhat confident from what I've met them and talked to them that this can work. If I talk more to people, I'm confident that I can make this work. Other questions?
Yeah, a comment. It sounds like you and I are sort of in the same boat, sort of, right? And it also, now I'm not familiar with the video for Linux, but it sounds like your Visual is a little bit similar to Null. And at least when I started the block layer stuff last year, the response was very much like we are not ready for this. And the response I get now is less no, right? So it's more of a maybe we can have a null block, maybe we can have it even existing alongside the C version, because if we're ever going to go this way, we're going to have something to look at like a first step. So I think these are the hoops that we're going to have to jump through, because we have a community that we need to cater to as well, right? Yeah, so I think it's a good idea.
I was expecting a more negative feedback from people, but they're actually open for this. It does have some restrictions. Yes, Julia.
So I've never written any Rust abstractions, so I don't know what they look like. But based on the question you asked, I wonder if there's some way that, like, if we're writing these abstractions, could we write some extra information that would somehow help people address this problem of how to keep them up to date and how to detect when they're out of date and so on?
So, well, one comment referring to the first question, also related to what Julia just asked. So what we cannot detect automatically, so we can detect for sure automatically if it does not compile, right? Which is what I was answering to John. So the problem I was referring to, that we can, so if it actually breaks, like it doesn't compile, we can detect that. I mean, the subsystem could have just, as part of the test, they just need to compile the code. They don't even need to run it, right? Now, there is the other layer, which is the logic things in the implementation that could change, that we cannot detect automatically. You would need more like tests or something that try to catch any kind of change there. And what we have been suggesting is two things. One is, of course, the maintainers need to be involved. They need to know when, basically, what they have, what abstractions they have on the Rust side, so that they basically catch the 99% of the cases and hopefully nothing slips. The other thing that we would like to do as well, that maybe some maintainers like, is adding a marker, especially for huge APIs, adding a marker where in the C side, a comment saying, well, there is an equivalent in Rust. It doesn't need to be anything else than a small one word, even a keyword, that then when you go to edit that thing, please know that there is something else somewhere else. That would help, maybe not maintainers, but it will help everybody else that needs to touch that code, right? Because maintainers should, in general, they should know what they have accepted in the Rust side, right?
We have that problem with C drivers anyway. Like if you change the behavior of an internal kernel API and you don't audit every single C driver in a tree, something's going to, and no one tests them all either. So it's like, yeah, we have that problem.
Yeah. We sometimes we say that, but it's true that it's also true. I understand the concern that in the Rust case, many people maybe is contributing, maybe not the maintainer, but other people that send patches to the subsystem, to the C side. Maybe they just send them. They are not aware of what is happening because it's experimental. They don't care about the Rust side. So I think it's a problem that will solve itself with time. It's just it's a concern that I understand that maintainers have. But I think so far what we have seen is that it's not such a big deal. The biggest deal is getting maintainers to get involved, I think, and to learn a bit of Rust, so they are confident on unbreaking, basically, not being. The worry is that, oh, I have to fix this. I have some color in the Rust side, and I don't know Rust to change it. So now, if I don't want to break the kernel rule of you have to, whenever you change in the kernel something, you have to change all the colors to match, right? So some maintainers worry about not being able to do that quickly, especially for, you get a security thing that you have to fix. You don't want to wait for the Rust side. And what Daniel is proposing, and what we discussed, is that if the video for Linux maintainers are really concerned about that, and they think it will block them, well, Daniel could offer, for example, well, I could be the maintainer. Well, one thing is that you can offer is, I will be the maintainer of that side. So you just ping me, and I will help you right away. So you have to commit, of course, or Daniel will need to commit to be ready to be on the spot to fix things, right? Another way is the comment in the thing that would point people to the Rust side, and hopefully they could then come to us. Maybe if Daniel is not around, they could, in the beginning, they could come to us to ask the Rust subsystem. They could come to us and say, hey, we need particular help here because maybe no one is answering. But in general, we need somebody on who to fall back, right? Another thing that Daniel could do is mark the experimental thing. It could be with a symbol, it could be with expert, it could be something else. It could be marked just as, not meant for users. It's just a reference driver, right? It's something that is to evaluate whether it's viable or not to have Rust in that subsystem. Even if, maybe not technically, but rather in the sense of, oh, we have enough people, we have enough resources to keep with Rust. So if we can have, even if it is a duplicate driver, which is another rule that we should not break, but I proposed in the Maintainer Summit topics, I wrote a proposal, and I was talking about it on Monday. We propose enabling maintainers that are willing to do so to break that rule of no duplicate drivers, only for the case where you want to have a Rust reference driver that you want to use for basically education purposes, for testing purposes, for starting the ball rolling, to get abstractions upstream, to avoid breaking the not dead code rule, and so on and so forth, right? So there are several options. Different maintainers have, when we talk about this with them, different maintainers reply differently. Some prefer that there is somebody, and they are happy if there is somebody in the maintainer's file, even if it is not their subsystem in another entry. That's fine. They say, okay, that's good enough. Some may say, no, we should do this more slowly, but they are open. Yeah, it's different maintainers, different situations. And in the case of Daniel, I suggested that maybe he could do one of these, and maybe the video for Linux folks are open to that. But yes, I think in these situations, the person behind the best thing they can do is commit, like publicly commit, okay, I will maintain this for at least, say, 1 year. I will be there. I will try to help you guys as much as I can. And then in 1 year, we will see where we are. And then the maintainers can decide, well, this worked or not, right? So we need to try. It's like the Rust experiment all in the whole kernel. This is like the local experiments in the subsystem, right? Exactly that, yeah.
And I commit, right? With
yeah, of course. Yeah.
Whatever I touch, break, I'm gonna fix.
Yeah. So of course there's a risk, and we also talked with yesterday. I was talking with another maintainer of not related to video for Linux. They were saying, yeah, but even if somebody commits, well, they can go away, right? That, of course, that's a risk. It can happen, but this experiment, if you declare it is an experiment, like for the Rust kernel experiment in general, well, if in 1 year the person has gone away or the thing doesn't work, well, we just take it out. There is no risk as long as we don't have users using the thing. And that's also the proposal. It came from these situations, Andreas, Daniel, and other things that we have been talking about. So I think the way to unblock is, as long as the maintainers are okay with at least trying, of course, is to offer this. Yeah. Any other feedback for Daniel? I think we have still time, probably.
Anybody have any other questions, feedback?
Okay, thanks a lot.
This is a nice problem to have, that somebody was so quick in the presentation that we don't have extra time. So, okay, I think we have 1 minute left. I think I will present Maria and Mayra, sorry, and then she's about on time to start. So she's working for Igalia. She's been getting involved in Rust and the kernel, and she has converted a DRM driver to Rust, and she will, I think, report on her experience. So yeah, whenever you want to start, I think.
So hey, I'm Maida. I'm a Gala developer that worked on converting the VGEN driver, which is a DRM driver, to Rust. And in this presentation, I have the intention to introduce you guys to RustGem and also to explore some problems that I have encountered during this journey. I separated a good amount of time so that we could discuss about like 10 minutes, just like Danielle, that we could discuss the challenges that we have, that we see the DRM, to see the DRM abstractions to be upstream, and hopefully we can come up with insightful ideas moving towards. So what is the VGEN driver first? VGEN stands for Virtual Gem Provider. So it's a virtual DRM driver. GEM, for those who are not familiar with the graphics subsystem, GEM stands for Graphics Execution Manager, and it is a memory management framework that we use in the DRM subsystem for handling graphics memory efficiently. So it is a hardware agnostic driver with no strings attached to any vendor, just like Danielle brought the idea. It's a virtual driver. It was written in C and introduced in the kernel in 2015. And it's a fairly small driver with about 400 lines in C. It provides a GEM service. As I told you guys, GEM is Graphics Execution Manager, and only 2 IOCTOs, one to attach defenses and the other to signal defenses. And the use case is when we don't have a real GPU available and we can create setups using QEMU and LLVM pipe. It can be quite useful when there's no real GPU and the graphic workloads have to go through LLVM pipe. So VGEN is a fairly compact driver. Why are we rewriting it? I mean, it could end in the same question that Dave asked us, like, why are we rewriting a driver? So rewriting VGEN was a proof of concept. The idea of converting a GPU driver to Rust was trying to answer in questions like, how suitable is Rust for the DRM? And are advantages in using Rust to write DRM drivers? And this is answering these questions is even more easy when we have an example to compare to. I mean, we have the C example. We can, compare to understand, it was easier. Did we prevent memory issues? Because while I was rewriting VGEN, for example, I could find some memory issues, like user-free issues in the VGEN driver. So we can compare two and see, those differences. Moreover, VGEN is a GPU agnostic driver, so we can really focus on the DRM framework and how to write the safe abstractions. We don't need to face any issues regarding hardware specifications or like weird firmware or things like that. VGEN really relies on the DRM infrastructure. So by using VGEN, we are making use of many aspects of the DRM infrastructure. So we are basically, by using the DRM abstractions, we are testing the whole DRM infrastructure via Rust. And VGEN is a fairly compact driver, so it would be a small project with very tangible goals. And finally, as I just told you guys, VGEN uses a lot of the DRM framework, so it's a great opportunity to explore the DRM bindings and see if they match the requirements of different drivers. As I'm going to tell you guys, I used Asahi's Linux bindings, and like using a Linux bindings in other driver proves that they are not unique to Asahi. They can be used for the many different purposes in the DRM subsystem. So the result of this idea was RustGen. RustGen is a driver written in Rust that has the exactly same functionality as VGEN. It didn't introduce anything new. I even used the same UAPI as VGEN. They have exactly the same IOCTOs, the same functionality. I wrote RustGen using Asahi's Linux DRM bindings and also some Rust for Linux bindings, especially the timer abstraction. And using the DRM bindings was really a really natural experience. I mean, even for a Rust beginner like me, it was really easy to use them, but it was a bit difficult to find some of the Rust for Linux bindings. They can be out of tree, just like Andreas mentioned, a bunch of them that are out of tree right now. But I must say that the community was really communicative and pointed me to the right resources. So I would really like to thank.
Can I ask a quick question? Because you said timer, so I'm curious. Is that the HR timer as well, or a different timer?
It's an abstraction for his abstraction.
Okay, cool. Cool. But that's what I mean. Like we need more, what you say, visibility in like who did what and where is it and stuff. Yeah. Thanks.
Yeah, it's some. I mean, by talking with the community, we can really find the bindings. I mean, he pointed me like, oh, I have the abstraction, but at that point, I have already wrote an abstraction, although it was a wrong abstraction. He pointed me to a much better abstraction, and I would really like to thank for all the Rust for Linux folks that are very communicative in Zulip. I would like to thank all the folks that interacted with me when I was writing the driver. It was really nice, and so thanks. Beyond the DRM bindings, I also wrote some bindings for legacy platform initialization, because VGEN is a virtual driver, so we don't have that like hot pluggable thing that we have in real drivers with platform devices. So not hot pluggable devices like VGEN or VKMS need legacy platform initialization, so I wrote bindings for that. And I also wrote bindings for DMA reservation objects. And apart from the bindings, I wrote the driver itself. You can access the code that I developed in the link in the slides. And finally, I would like to share with you guys some of the challenges that I have encountered during this process. So here I must say that I'm going to give the perspective of a C programmer. Like, probably the answers to these questions might sound really obvious for like experienced Rust developers, but I would like us to use this space to document these ideas, for future reference. My first challenge in dealing with Rust in the kernel environment is managing unsafe code. Like for me, like beginning in Rust for Linux, it looked like a loophole, the fact that we need unsafe code to write the safe abstractions. Because The whole point of moving from C to Rust was to avoid trusting on people to write safe code. And here we are again, like trusting on people to write safe code. And by the end of the process, of course, I could understand that now we are minimizing the amount of unsafe code that we have in the kernel. So it's a win after all. But we still have, in a smaller amount, the problem of trusting on people, which means that we need safety review. And from what I could see, like the Rust for Linux folks are really engaged in, safety review. You guys are like very experienced Rust developers. So you are like making your best to review like every Rust patch related patch. But sometimes not the subsystem reviewers are that engaged in safety review. So the first question that I would like to raise to you guys is, how can we encourage safety review inside the subsystems? Because this can be a problem in the future. Because sometimes the Rust for Linux folks don't have the expertise needed. You guys are very experienced developers, but sometimes you don't really understand the concepts of a very specific subsystem because the kernel is huge. So how can we engage those like old school C developers to properly review Rust code? Because, to just read Rust, we are programmers, we know how to read things in many languages. But to see the subtleties of the languages sometimes is not that easy. So it's something that I would like us to think about, to...
Do you want that we discuss one by one or later?
We can discuss later. I gathered all the questions in the final slide, so we can discuss later. And this brings me also to a second question, like, can a beginner spot subtle safety issues in the code? Like, I can say for myself that I wasn't. This is a code snippet in the slides. This is a code snippet of a code that I submitted in the VGEN RFC. And this small code snippet has an issue, although it has a safety comment. And it has a safety comment because I thought it was safe, but it wasn't. Like Bjorn pointed to me during the review process, there is nothing ensuring that DMA reserve doesn't outlive self and thus may be deallocated. So, although I thought this code was safe, it was not that safe. So I believe that we need to think about approaches to make sure that Rust in the kernel is accessible for beginners, but not to the point that they might be introducing safety issues in the kernel. And a second challenge for me was how to write good abstractions. There are a couple of specific patterns that are used when writing safe abstractions that I wasn't familiar with, at least. And the mentorship session that I linked on the slides that Miguel gave, it's a very good resource, but I believe that we can do even more. I thought that, what about writing more documentation about writing safe abstractions? Sometimes we don't even need to write very formal documentation. We can write like a blog post documenting the process of writing an abstraction, like just sometimes like a journal, something like that. This way, we can build more knowledge about safe abstractions, improve safety review because we are building more content about safety safe abstractions, and bringing more people on board with us. And finally, a more technical question: how can we make macro expansion easier? For example, I had these two macros in the VGEN UAPI that I had to turn into enums so that they could be solvable by VGEN. And this is not ideal. I would like just to use my macros, don't touch on the UAPI would be ideal for me. So I would like to raise these questions to the Rust experts in the room, like, could we make this more like easier? Maybe something in VGEN, And apart from my technical challenges, I would like to bring a more broader discussion. At the moment, in the DRM, we have the DRM bindings, like that were written by Asahi Lina. We have two almost upstreamable drivers in the DRM. We have Asahi and we have RustGen. What could help us to upstream Rust for DRM? Like, are we lacking reviewers? Are the maintainers not willing to maintain the DRM bindings? We don't want Rust in the DRM. What is missing? What is the next step that we could need to take to move into this direction? And like, if we finally take the next step, it means that everybody is responsible for it. This means that we cannot have C-only developers in the DRM, like, nor we can have Rust-only developers in the DRM. It means that everybody is responsible for it. So if I'm going to touch on C code that affects Rust, I need to be responsible for the Rust code as well, not only the C code. It's my problem as well. I mean, we are a community. So this also means that people writing the Rust bindings might need to touch on C code. And it's not reasonable to expect that a Rust developer will be able to guarantee all safety requirements without touching on the C code. I mean, sometimes you need to, for example, Danielle pointed that they have some lifetime problems in the C side, right? So how he's going to just solve these lifetime problems in the Rust side without touching on the C side? It's not possible. So we can even see the bright side of this. I mean, a Rust developer will be working to make the C code even safer. So, I mean, it's great for all of us. So if we want to see things moving forward, I believe that we need to learn how to compromise between those two sides. And this way, we are going to have the well-documented benefits of Rust spreading around multiple subsystems. So I just gathered all the questions that I raised during this talk. I believe that we have like 10 minutes that we could now discuss. I would like us especially to focus on the bold question because, I mean, as I told you guys, we have the DRM abstractions, we have drivers, what is missing?
I have absolutely no problem with putting Rust drivers in the DRM. I'm perfectly happy that we put Rust drivers in as many as possible in the DRM. I'm fully behind this effort. I'm not a Rust expert. I can read it barely, but yeah, to upstream this, right? The Asahi thing has hit a bit of a roadblock, and that's a problem I'm sorting through now. I'm trying to assign engineers to work on that, and that's a lifetimes issue at the scheduler level. That's really messy lifetimes. The lifetimes in C are already all over the place, so we will get that solved. This driver, I don't really see anything stopping it other than somebody with Rust saying that those abstractions are safe, and yeah, and we should just try and get it in the tree. I don't mind having 2 copies of something in my tree. I don't mind getting rid of the VGEN if this is in any way better, even in any axis. VGEN is not a driver we really care about. So it's like, yeah, this is better. We'll kill it. Like it's so, yeah, I am fully supportive. Do whatever we, if someone's blocking you, come to me. And I shall resolve it. Yeah. Definitely want it.
Starting with RustGen would be like a pretty nice idea to, start because RustGen doesn't require all the Asahi Linux abstractions.
Yeah,
so we can like pick a couple of them, start to make the upstream and, start to integrate into.
I'm also good with carrying a bit of dead code for a release, 2 releases. I can understand there's going to be some non-DRM abstractions we have to upstream. I'm also willing to help if they need velocity and pushing, because yeah, like I can merge stuff through my tree. I don't really care. I'm
just one comment on the reviews from C maintainers. I posed the same question as well, and it seemed like the answer made perfect sense to me. And they told me, I don't need to trust that your Rust code is going to be right the first time. I need to trust that you'll be there to fix it, and that's it.
Okay, I try to answer the first two questions. So Benno said in the chat that Benno is already working on something like a safety standard for like all the safety comments. So in the future, you may not just put a safety comment saying, "Hey, I believe it's safe." You cannot do that. You must have like a reasoning about that, and there will be some kind of criteria for you to to think about it before you put on a safety comment. And also, when you expose something unsafe, then you will also think that I have to require the user to prove that there are some certain like safety condition is met for this function for the use to be safe. Okay, so that is working in progress. That's something working in progress.
Yeah, but I believe that this connects to the first question, like how can we document the process of the thinking about the safety review? Because I put some reasoning into all my safety reviews, but I mean, I'm a human, I make mistakes. I mean, I'm not that experienced developer. So how can we maybe create more documentation on how to analyze each safety comment?
So the purpose of the like the safety the documentation that Benno is working on, and also I'm working on something called reverse recommendation, is to give people's like handbook they can follow on to do the review, so that they can this is something I need to check. But like obviously, like we may like when people use that as handbook, still could be something could be missed. So we will need to keep to improve that. But this is something we try to like provide to everyone, so that you don't need to be like you can do that on your own. Like you have some certainty about that, the safety of your API or your abstraction. But I want to mention that. Go ahead.
No, so I just wanted to. Okay, so I just wanted to talk a bit about what I'm working on there. The thing is, it's very difficult to have both humanly easy understandable safety documentation and still rigorous definitions that you cannot misinterpret. And as you said, you still can have mistakes in there, and I think that's just where we have to rely on review as the C side also does. And I think the important thing for us to notice is that the unsafe code that we have is similar, has the same vulnerabilities, or essentially the code itself has the same problems as the C code as well, where we have to catch things in review. But with the safety comments, we can ensure that if you read it like more or less like a formal system, then you can ensure that it's correct by just following some certain logical rules there. And in your case, the important thing is that the safety documentation of the function that you had there would have required that you pay attention to the lifetime of the object. It would say that you would also have to ensure that the object that you create from there lives as long as, or the reference that you put into there lives at least as long as the thing that you get out.
I just wonder, would there be value in also sort of documenting the bad things, the anti-patterns? That, like, if you spot C code that looks like this, well, you're not going to make it into Rust. You need to fix C code, like getting that sort of thing out there.
Yeah, we're trying to get that thing out, but like object in kernel are like there's like various of object in kernel. Some of the object have this attribute, some of that has that attribute. So we right now we only allow to upstream the abstraction that have a real user. So what the ideal is that we can do like more abstraction work, so that we can learn that, oh, this is like a certain thing have the certain pattern. But we're going to learn it one by one, like learn it. So we are going. So it's going to be a learning process. But we are trying to like make something that everybody is easy to follow, at least to make sure that there is no obvious known issue. Yeah.
If nobody else wants to speak, I think just to address the thing you said about macro expansion, I think that's a known binding bug. So if you look for issue 731,
it was fixed.
it wasn't. There was somebody commented on it today by coincidence, but I don't think it was fixed. So the answer for your question, I think, is no.
Yeah, I thought I knew that it wasn't fixed. But I would like us to, I mean, there are a couple of Rust experts in the room. They might have some ideas.
It's been 3 years. I don't think it's.
Yeah, you were the Rust expert that I was looking for.
What?
You were the Rust expert that I was looking for.
Oh no, not me. I'm sorry.
These changes where we use the enum instead of define, maybe we should just upstream those, even if they come before the Rust code that needs it, right?
Right.
I mean, maybe that's reasonable enough to do that in the C code anyway.
Yeah, I mean, for me, it's reasonable, but maybe someone could say that we are touching on the C code. I mean, you shouldn't be touching on the C code.
So one comment. So it's not. I don't think it's considered a bug because basically a feature that is missing. They don't go into the macros as soon as it's not trivial. They bail out and that's it. Okay, so they want to potentially have solutions for that. They want to increase. I know that the binding maintainers are interested in expanding more of those. So basically, the idea would be to at least get to the ones that expand to a constant, right? So at least handle those, right? I think would be very nice for us. Now but I have a few comments on the other questions as well. On touching the C side. In the beginning, it's true that we were trying when we were out of tree and we were trying to show how Rust would work in the kernel. We were trying hard to not touch any C side code in order to precisely show that it could work even in that case. Now, talking to maintainers and talking to the C side maintainers and so on in the last year, we have seen that they are willing to improve things on the C side if that makes things easier on the Rust side, at least some of those, right? And that's very nice because then it opens the door to other solutions. I mean, not just in this binding thing, but in many other design things that you can actually make the thing easier on the Rust side if you can at least have some flexibility on changing the C side. Another thing on the safety review, I think, what June covered that is, what I wanted to stress is that, as Ben was saying, this is something that we have in the C side. So basically the question is, hey, we have nice comments there that explain why it is okay. In the C side, sometimes we don't even have those. And the problem that we are having now is, hey, can we formalize those to make it even easier to review or automate some of those reviews? So basically we are trying to solve problems that we create for themselves when we try to do things, how to say, more documented or more properly. But of course, we can make mistakes there. At least right now, we don't have a formal tool that can verify the safety comments, but it's exactly the same thing as in the C side. So it's an improvement. What we believe is that it's an improvement over C already, even if we didn't have anything else than the safety comments right now. That could be mistaken. You see. More things. I think. Well, they've answered the upstreaming. And how can encourage safety review inside the subsystem? Now, a comment that Dave said. That's why I was saying that before, that we really need the maintainers to learn Rust to some degree, because there are many things, and you were pointing out, hey, the Rust people is doing, Rust for Linux people is doing these abstractions, but really what we were doing so far is trying to do prototypes to showcase how it would look, how it works. But in the end, what we need is the experts of each subsystem to understand the code really and how Rust works, to say, hey, this is actually matching my expectation on the C side and how the lifetimes work on the C side. If they don't understand Rust, it's not going to work really well. If we write abstractions, we are for sure going to miss something unless we have like a long chat, like a Sahilina had with DRM people chatting. Oh, okay, this works like I expect. This doesn't. So in the end, as we have been saying, and we have never said otherwise. Some people tell us, oh, but you are going to have issues with this. No, we have said all the time, if this is going to work, we need the experts to know Rust. And there is no way around it. And I don't want to hide that fact. Like, if you have a complex system where lifetimes are complex, the relationships are complex, you really need the maintainers to tell you, okay, this is actually what we want. Because in the end, what you are encoding is extra things that C cannot encode in types, in signatures. What you are doing is encoding that knowledge into those. And that's what we need somebody to tell us, hey, what you have encoded is actually what is the reality, right?
Yeah, to echo that a little bit, as a maintainer of a subsystem with a very small amount of Rust bindings in that init with KUnit, the way there, because I'm not going to pretend to know even anything more than the very slightest amount of Rust doing that, is it's difficult to learn Rust while you're busy doing maintainership stuff. The kernel is not the easiest place to learn Rust because, the sorts of things you want to do in the kernel, and particularly as we're talking about writing abstractions, which is one of the hardest things to do correctly, are not typical beginner Rust things. And you go out and look at external Rust documentation, and, every time you try to look up how to do something you need to do in the kernel, the response is, don't do that. You only need to do that if you're doing something crazy like working on a kernel. So I think, one, it will be great to improve the amount of documentation that we have that is how to learn Rust and kernel, Linux kernel focused. I think we're starting with that and we're going to get there. Two, we have lots of people, in the Rust community who are prepared to help out as, co-maintainers, to accept, hey, I'm reviewing something with some scary abstractions in my subsystem. As a Rust expert, can you have another look over that? And three, if the bindings, if it's not perfectly safe the first time we accept it, I don't think we should block waiting for every binding to be absolutely perfect. We can send another patch out to fix a safety issue if it comes out. Let's not make that something that we totally stop everything for.
No, I think we're right in that. I'm willing to let people make mistakes. It's fine. Everyone makes mistakes. We're going to have to make mistakes. It's not going to go forward otherwise. But yeah, one bit of feedback I did get from one of my maintainers recently about it was his worry was, and this I don't know how is that he would start writing Rust like C. He would end up with a lot. And I think doing the abstractions, and then we do these small 200 and 400 line drivers. So when we get to the 10,000, 20,000, 30,000 line drivers, you're getting that Rust. Writing Rust as Rust instead of just writing C in Rust and getting that mindset change. And I think, again, it'd be useful to have some resources around, is this Rust type, or should I be thinking more about objects and, things like that.
Definitely. And we have been a bit not trying to reach perfection because that's not good. We have been trying in the first abstractions and the first things that we have streamed, we have been trying to be slow and cautious and try to set a good example. And for example, things like you are mentioning, one thing that we do, and this relates to something that was discussed before in John's talk in the documentation, is documentation. Take documentation, for example. We are requesting for Rust code that things are documented and things have examples that are compiled and tested as KUnit tests, thanks to thanks to the KUnit guy that accepted that doc test framework. Now, what I'm trying to say is that we have some stricter rules for Rust code, and we would like that those apply to all the kernel. And we are trying to say, hey, let's be a bit more strict. We don't need to be perfect, but let's try to set an example. So the first maintainers, we hope that they try to follow the things that we have been working on the last years and try to follow that example, because I think it's the way to basically get everybody else to see how to write that Rust code. Oh, the Rust code has to be documented. It has to follow the same style. It has to, you shouldn't write unsafe code for no reason. You have to put all the safety comments there. All these things that we have, not rules, but well, some of them are rules, or we want them to be hard rules, like don't submit something that isn't documented, and the compiler will complain you don't document it. But even if there is a set of things we want to improve over C, if possible, right? And we know sometimes maintainers have told us they are closing on us, they are looking at us. So some maintainers told us, well, this is too much, maybe. Okay, like no way, we don't really do, we cannot do things this way. It's not that we want to force everybody to do it that way. What we want is that we are cautious in the beginning, and we set an example so that others can, because the best way to learn is to see what has been done before. The first thing you do is go, oh, let's check what the others did, right? So we need the very first ones that we get into the kernel to be as proper, if you will, as possible, and as perfect as possible. Of course, we don't want to reach perfection, and we know we need to be practical, and we need to go forward. And if there is a soundness issue, safety issue, that we should, it's not the end of the world. In fact, some of the soundness issues, even if some safety comment is wrong, and there is a way to sneak some safe Rust, in C, that's all functions, basically. So I mean, it's still some issue that you may not have any caller in a user that is actually having an undefined behavior as memory safety issue. So it's like this extra layer that we are talking all the time about. This extra layer is what is really worth about Rust. And that's why we want to get that extra layer to be really, basically to get it into the minds of the developers and maintainers that we really need to preserve that. We need to avoid putting code. What we want is that the key point is don't put, if you know there is a soundness hole, please don't merge the code. Even if nobody is triggering the undefined behavior through there, but please fix it before putting it in, because that's the layer of protection that Rust gives you. And to the point that we want to backport even soundness hole issues to stable kernels. You see, even if nobody has an issue, and the stable kernel rules say, hey, it has to be a real issue. Even if it is not an issue because no caller is doing it, we still want to try to backport all those fixes into a stable, because somebody maybe out of 3. So we want to really make the point that these things need to be fixed. Like, they are really issues, even if they are not triggered. Sorry, go ahead.
Yeah, I think we can maybe use this to our advantage, just to make overall things better. When you're writing Rust abstractions, there's a lot of areas where it is very tricky, and come to the list and say, hey, this doesn't make sense. Please write documentation, because I do not understand how this interface is supposed to work, because I know that the code is the documentation, but there's a lot of cases where it's just incomprehensible. And if we can make that better in C and in the documentation, then that makes your lives easier, it makes our lives easier, and then we all understand what's going on. So if that's good motivation to improve our documentation, then I think we should go for it.
So I haven't written any Rust code yet, but I'm very interested in exploring Rust. So one thing, I have a question regarding this unsafe code. So would writing more unit tests around the unsafe code would help in catching this safety issue, like safety comment that we are writing around the unsafe code?
It can help in the sense that, for example, if you trigger an assertion, you trigger a debug assertion, you trigger, or it just breaks, it can help. But what I would say is that for at least, I think, unless you have a very thorough testing thing, and even in the case, you may still, because you may not have any caller even in the test that exploits undefined behavior. But attackers or hackers that are going to try to find those, maybe they find a way through the things that you have. I don't know. Well, just to clarify, what I mean is that you may not have callers. If you don't have any callers that is triggering the issue, you don't have any vulnerability. Okay, but still, I think for fixing those things, we could have something like UBSAN, something like that that is mirrored for Rust, and ideally we could be running our tests under that to be able to catch these things as well. But yeah, I think it's a matter of, it has to be an expert that knows what are the lifetimes and what are how the objects behave. Yeah, I don't think the documentation helps in the sense that it helps people to think about it and say, hey, no, this is not the way it is. If you don't have any docs, I think it's easier to just slip through. If you just merge code, and that's why we put a function in the docs.
Yeah, just one thing on this topic. Along with documentation, I think it would help to improve the debuggability of the Rust code. Let's say, for example, I don't know, there's a kernel oops, kernel panic, there's a trace. The Rust functions have all the mangling, and for me, it's quite difficult to see from the trace and get back to the code. Another thing is in C, I have access to a wide variety of tools, like let's say BPF trace or other in-kernel sanitizer and whatnot. That's something that, if there are plans on supporting these tools, I think, it will help a lot.
We are over time. We have to close, there was a question about if you can provide maybe in the slides the correct code for that snippet.
Okay, I
It would
can
be nice.
upload this with
Yeah.
the correct.
Thank you, everybody, for coming to RustMC. There are some gifts for the speakers, so please stay around.